Hello, everyone. So let's start with the last lecture on atomic quantum optics. And now the speaker is Daniel Sahagun, one of the organizers of this school. And he is from Institute of Physics here at UNAM. So he's a local. And he's going to talk about atomic quantum optics inside the system of photons and atomic ensembles. So please, Daniel, go ahead.
Thank you. Can you hear me? Yes? Okay. So I'm glad we have made it so far. It's been a long week and I'm enjoying very much and I thank you all for coming and being part of it. I'm also an experimentalist. We decided yesterday to take a group picture, to update the group picture. And okay, we wanted to show the lab, but you saw it presumably yesterday. But mainly, we wanted to show that we do also have cables. Lots of them. So that's it. Experimentalists have cables. So this is, as Ricardo said, this is the last talk about atom quantum optics. And I want to somehow summarize what we have seen. We have seen how about the development of how we can dominate, we can control the external degrees of freedoms of atoms. And then we can use them to make many things like Bose-Einstein condensates, droplets with this very nice picture that Rocio showed to us. And then we also saw some applications like constructing optical instruments for matter waves, quantum simulations, and so on. Later on, that has been mostly Morgan talking about, is how we can make most of the exquisite control of the internal degrees of freedom. And he spoke about metrology yesterday in a very interesting talk. And now I will talk about how we do use the spin to manipulate information, quantum information. And the application that I will talk about is quantum networks. So when I was a PhD student, I read this paper from Geoff Kimball that actually I want to mention. He passed away, unfortunately, last year. When he was quoting the quantum internet based in photons and atoms. At that time, it was 20 years ago, a little bit more, maybe more. He was talking about making the most of the fact that atoms and photons can interchange information and then use that to create a network. At that time, I more or less thought that it was science fiction, but now I'm realizing that that's going to happen and that's the way internet will turn to. So what's the quantum internet? This is a beautiful artistical view that the Alliance, the quantum internet program of the European Union did, in which they illustrate that the main point of having the main difference between the internet of now and what it's going to be is that you also have nodes, as we do have now, and you also have messengers of information, as we do have now. The difference is this little arrow that we have in every node. That little arrow represents a qubit. And all these qubits are meant to be entangled. So that's the main difference that's the main difference of the requirements of the architecture of the quantum internet. And it's happening actually in China. They have already this network that covers thousands of kilometers literally thousands of kilometers, and in which they don't quite have a full quantum network, but they do have a quantum key distribution network. So they share secrets between these nodes, between cities, and then they even have, they even put a parametric down conversion source of entangled photons on a satellite already a few years ago, and so that they are distributing entangled photons and then performing protocols of security protocols. This, it seems like in China, in Asia, they like a lot of quantum key distribution. Even more, well, in Singapore, I just came across that they have even developed an educational kit. So it's been part of already, it's accessible for teaching and for learning in an early stage. So this is, if you look up S15 instruments, it's a spin-off of Christian Kurstiefen, who is a researcher in the Center for Quantum Technologies of the University of Singapore. And actually it's quite cool because you have Alice, Bob, and the spy. And it's just $5,000, Sing dollars. And of course, you need 3 computers to play. But anyway, it's good. I already told our director to buy me one. She said, as long as there's money, we will, and I'm very happy. So when I looked up there's something that I'd like to point out. When I looked up the picture of the group of Christian, I realized that Vindhya was there. Vindhya is a former PhD student of Morgan, and it was the very first master's thesis that I helped to revise. And then there's another overlap. He is a very good friend of mine, Alessandro. He came a few times to help us in the lab from Singapore, and he is also a former postdoc of Morgan. So it's been some interchange through Singapore, an interesting interchange with his group. Anyway, back to business. So there's another example. There are different scales. Of course, not everyone has that much money as China, but in Holland, they have this little network with 3 nodes, with diamond, with nitrogen vacancies, diamond with nitrogen vacancies centers, in which they do have also the characters of quantum information, Alice and Bob, and also they do have a third one, Charlie. And they perform long distance entanglement. You can imagine that if you are talking about a very small things, 30 meters is already, if you manage 30 meters, you're already doing good. And then they do have a memory. So in summary, to create a network, you need nodes that can be memories, or memories that you can trigger and release photons. You need a source of entanglement, and you need quantum channels, which are photons. This is another example, and this one actually has an a fully atomic platform, technological platform. This is being placed in New York by several collaborations of university. I believe it's the University of Yale and Stony Brook, and there's another one. Anyway, and here I want to point out that even though you manage to make all the nodes that people are already managing to do, which are memories or your switches, you also need switches to distribute the information. The main challenge is to do a quantum repeater. We will not go through that. It's very interesting, it's lengthy. But I want to point out that this this is a very nice challenge that has been running for about 20 years that is forcing us to push the field. So also is the University of Columbia is over here. Also, that was the third one that I was missing. Anyway, in this talk, we will have a little revise of what are qubits, what is a qubit, because I'm sure there are people that have been afraid of asking what is a qubit, because everyone seems to know. Good news, not everyone knows, and everyone knows. So let's revise it a little bit. It's important to realize at this point that particles with mass and particles without mass can be a qubit. And that's the key of hybrid quantum systems, in which you can interchange between light and matter information, and that's the very basic unit of information is the qubit. Okay, we will go through the relevant through the relevant examples for this talk. We will be talking about how we can see polarization of light as a qubit, and I will retake Morgan's revision on the block sphere, and so you can view a two-level atom as a qubit. Well, he was speaking as a spin, but pretty much anything that can be called a spin is a qubit. Then I will talk a little bit about how you can generate qubits with light, and also how can you generate entangled qubits with light. And at the end, if I have enough time, I will revise a little bit some protocols of storage of light of qubits with atoms. On the way, I will be using as an example the work that we're doing in the lab. So if you like to know technical questions, you can ask. Okay, so what is a qubit? Imagine that you have a black box. That black box in quantum mechanics, we call it an operator. And you have an arrow that you don't know which orientation it has. It doesn't necessarily is facing up. It could be facing anywhere. Then you take a measurement, and if it's parallel to the orientation of your box, then it will give you a +1. And if it's not, it will give you a -1. At this point, you could tell me, okay, this is a dot product in the classical physics, and that's it. And you're right. But there are some coincidences with classical physics and quantum mechanics. Let's not forget that the quantum mechanics is a limit of classical mechanics and the other way around. But if you turn around your frame of reference, your box, then in this case, what will you get? Well, the answer is sometimes you will get a +1, sometimes you will get a -1. In that sense, you don't have a correct answer unless you do it many times. And those are the clicks you have in quantum optics. All the information that you get of the quantum modes, of the quantum states, you get it by clicks. And that's what you see in the lab, clicks. And at the end, why you have random, why do you have random answers? Is because you have the superposition principle, and that I'm sure it reminds you already. Most of you know about these states, and then the coefficients, which they give you the probability of finding the state up, and or the state down. Then you have to square that, and that gives you the probability. And that is the power of quantum information. With just two levels, you have an infinity of options to encrypt information, because these numbers can take take any value from 0 to 1. Okay, so let's recall a little bit our classes of electrodynamics and remember about polarization. And here we have a wave traveling with linear polarization, and you have two planes, and then you travel as you go. And this is what we will see how this can be looked as a qubit if you quantize the field. And then we will recall the two atom model to call, so you can place it in the Bloch sphere and call it a spin. Okay, so the polarization. Let's see. Everyone remembers. I'm sure everyone remembers these expressions for the undergraduate courses. You have linear polarization and circular polarization, and then you see that the bases relate with these equations. Does that ring a bell from yesterday? Anyone? No? Okay. Let's see if we manage to recall. Okay. So if we think about the Poincare sphere, which is more or less, it's pretty much the same as the Bloch sphere, you will realize that we can undefine the Stokes parameters. Then it's an equivalent way of visualizing the state of polarization. And the good thing is that the Stokes parameters will give you exactly the coordinates on the sphere that the vector or the polarization vector points in the Poincare sphere. So note that at the equator, you find linearly polarized light, and then you add ellipticity as you go far from the equator until you get circular polarized light with opposite directions in the poles. And also note that you can actually go through all the points of the sphere with this little device of this little array of optics. Here you have a lambda over 4, then a lambda that to control the ellipticity, then a lambda over 2 to change the orientation, and then you can divide the two components, and that's how you can manage to measure and control all the parameters that you need for measuring the Stokes parameters, and this is called a polarization analyzer, and that's it. So remember the sphere, the Poincare sphere. Now we will go. We will make a very fast review of what Morgan saw yesterday, in which you have a two-level atom with energy 1 and 2, each state. The difference of the energy is h bar or omega 0. And then you have a two-dimensional Hilbert space, which means that you will always have 4 linearly independent operators. This is a common base that you can use for that, and it's normally useful to define these Hermitian operators. So then you can have all the relations of angular momentum, and that's also mapping onto a sphere. So then you can realize that there is a good mapping. Well, this is the possibility of map what you measure here and you measure here, and that makes you wonder whether you can actually send a point in a controlled way from this sphere to this sphere and the other way around. And that answer is, in principle, it might be true. The most honest answer is that we would like to. And the most honest answer is that we have very little control yet. Okay? And so I will, in the rest of the talk, I will tell you a few things that are limiting our control and how we could improve it. Okay, so let's go back to the two-level atom and solve it with the Schrödinger equation. But now, in order to create some dynamics between the levels, we put a laser. And we defined a new variable in our experiment, which is the laser frequency and the detuning of the laser frequency from the resonant frequency of your two-level atom. Okay, so then you start with the stationary state that everyone knows, but also consider the atom and laser coupling, which is given by this term, where this R is actually the position of the electron. That is that in the case, well, in principle, it's all the electrons, but if you have an alkali, as we do, then you can think about just one electron. Then you insert what you have into the Schrödinger's equation, and you can more or less easily solve for each one of the coefficients, and that's what you want. Once you have the coefficients of your wave function, then you have pretty much everything. And it's important to mention that all the constants you can group them together in this omega 0, which is called the Rabi frequency on resonance, which is the matrix element of the position of the electron with the two states that you are driving the atom through, the charge of the electron and and it's proportional to the electric field, to the magnitude of the electric field, and it's over h bar. This Rabi frequency is going to be important because at the end, when we consider spontaneous emission, it will give us the rate in which the atom is oscillating from one state to the other. Okay, so here's just a little reminder about the matrix density. Yesterday I saw that everyone raised their hands when Daniel asked about who knew about it, but I just would like to remind you how to calculate the matrix elements, and that you can separate them between the diagonal, which the trace of them should be 1, sorry. And then the off-diagonal is how to calculate the off-diagonal elements, which they will have also a meaning. Okay, so also not to be worried, because we will solve a dynamical equation for the density matrix operator. This is also a little reminder that then with a unitary operator, which is actually this exponential, you can track the evolution of time of the states, and then with the same formalism, you can extend that to the evolution of the matrix, density matrix, the evolution in time of the density matrix. Okay, so since we already know how to calculate all the coefficients and the matrix elements, okay, we do it. We see that they are in terms of the coefficients, which is good. And then if we are interested on the dynamics, what do we have to do? We have to differentiate. Here I want to point out the meaning of the diagonal elements. The the diagonal elements are called the populations of the states, meaning that if you had many atoms, if you are applying this Schrödinger equation to many non-interacting atoms, then this will be the number of atoms in the base state, and this will be the number of atoms in the upper state. So that's always a good thing to check. If that some of them they don't, is not one, then you are in trouble. And then the off-diagonal elements are also pretty important. They are actually the elements in which you can see the interference between the stomic coherences, and that's the base. The existence of these elements is the base of atom interferometry. So it's very important to have that in mind, so you can understand what's going on in atom optics. Okay, so what to do next? We could take, since the same system as we solved with stationary states, we can take the coefficients that we calculate with the Schrödinger equation, plug them in the equations that we have for each one of the matrix elements of the density matrix, and then solve it. And we will, we can apply the rotating wave approximation, which, not to be scared, is just, I think Daniel already mentioned it yesterday. Did you? Yes. Okay. And then you get to two equations. That one tells you how the population balance drives itself. And this is important, for example, for a population inversion, and that's important to understand how a laser works. Then, for the atomic coherences, you see that the difference between the populations is important. The balance between the populations, for example, if this is here, you have no dynamics. Okay? Then, okay, but we are not complete yet. The atoms are in contact with the modes of the vacuum. And those modes also generate decays from the decays that we are going to take in account with this coefficient gamma. This coefficient gamma, maybe some of you in your undergrad courses remember of the Einstein's coefficient. Is pretty much the same as the B Einstein coefficient. And when you take in account the vacuum, you are talking about the open quantum system. And then the Schrödinger equation is not enough to give you all the information of the system. And then you compulsory need the density matrix. There's a quick fix for that, because you will say, okay, then I throw to the rubbish all my work, but no, it works if you just stick it in here in the solution of your. We are not explaining spontaneous emission. This is just a quick fix that you can do, and it works. And then your population balance and atomic coherences look very similar, and that's a quick way to actually solve the problem. But guess what? If you are in the lab, you cannot just do that. You have to take in account the atoms are not, well, if you are talking about ensembles of atoms, you need to take in account how far are they from each other. And the reason is that when you are driving a transition, you are creating dipoles in all of them. And those dipoles have a field. And every dipole feels the field of the other dipole. And so if you have them close enough, that can be very significant. and then okay, and that gives rise to modify quite a lot the radiation that you can generate with just these two single this system of many two-level atoms. So the difference is that when the dipoles are emitting coordinated, it seems that is called to be they are coherently emitting. So instead of just having a spontaneous emission to light everywhere, you have light also in a directed way. You find you find a spot of light. Let's say if you see that the atoms are shining in a sphere, you will see a much brighter spot in that sphere, and that's a signal that the atoms are coherently emitting. You can this problem is quite it's not recent, it's quite old. You can see the formality in this very nice review by Gross and Harosh. And I actually find a little bit funny that Harosh was into that in the 80s, but then he got the Nobel Prize for controlling single particles. So it seems like he thought it was the problem that it was too hard, and then he won the Nobel Prize doing instead of considering a lot of atoms, just one. And it is a big it's a difficult problem. It's actually a bottleneck in the field. And mainly you could think of three regimes. The first one, you see all the atoms emitted everywhere. Then you see if it's not that dilute the gas, then you can see forward as we will see in four-way mixing. You see forward emission, and if the sample is too dense, then you will see phenomena like superradiance and subradiance. Okay, so what do you measure? You are in the lab and you need to understand what are you going to measure. So what do you have? You have a cloud of atoms, and you have a detector, and with your detector you can measure intensity. That intensity has an operator assigned to it, which is this product. And you can, what we measure in the lab is expected value. And we all know that from the density matrix that if you manage to calculate the density matrix of the atomic system, then you can multiply by these two operators and get what you want, the expected value of the intensity. That's in the other hand. Note that here I'm putting the density matrix of the atoms. But you can also just say, okay, I don't care where is this field coming from, and measure the density matrix of the light. And that you can do with the stock parameters through this relation. And when you need also these matrices, they are basically the sigmas are the Pauli matrices plus the unitary matrix. Okay. And also it's important to understand that, for example, if you wish to measure horizontal light or the horizontal component, that you can fix it with the optical array that I have shown to you before. So basically, this is the operator that gives rise to this measure. This is if you quantize the light, then you are already doing quantum tomography, and if you'd like to revise it, this is a very good place to go. It's a very lengthy I believe it's a chapter of a book, and also another one is an article, and they go through it very, very, very thoroughly. Okay, but we're looking at how to. You will tell me, okay, this is atoms shining light, but what is quantum about that? Okay, and there was also, you can see anti-bunching in what I told you, but you can also, with atoms, create entangled light. And actually, these guys, Alan Aspect and Clauser, got the Nobel Prize for being the first of demonstrating that you can do that and actually show that they are entangled. And this is a little bit of how they did it. In both cases, they used calcium atoms, and then they did an excitation to a second excited state, and some conditions that I will tell to you in a minute, that to the case you can prove that they are entangled. So this is the experiment of Clauser and Friedman. This is the first experiment of Alan Aspect that he made them many improvements to search for loophole-free measurements, mainly with technological improvements. And here the most outstanding, well, the improvement that points out at the beginning is that instead of using a lamp of UV, which they did here, they already used lasers, dye lasers, and that made a big difference in the violation of the Bell inequality that they measured. Okay, what do we do in the lab? What is keeping us quite busy? So we're into that. We are generating light with a diamond scheme, which is basically what we saw here. We make a double excitation. The variables that are important is the intensity, the polarization, and the detuning of the lasers amongst the other states of the states. And then what we get is a signal and Hitler's photon. It's important to notice that in spontaneous emission, we were talking about Chi1, but in order to have this process called four-way mixing, you need central symmetric symmetry is associated with Chi3. And then you can see that the polarization of one of the frequencies, let's say 1, as an emitter of light of frequency of light with frequency 1 as a function of the product of the other 3 fields. Okay? And you will find quantum correlations as long as they fulfill conservation of energy and conservation of linear momentum, which is called the phase matching condition. Okay, so let's go to real life. Well, maybe the lab is not really the real life, but this is rubidium. This is also our favorite element in the lab, and it's we use these transitions to this is called the. This is wrong. This is the D2 line. This is the D1 line. We go up through the D1, D2 line, then we go up again until the 5 2/3 state, and then we look to these two decays. And this is a picture with a normal camera of the cloud. And who would like to guess why we see it blue? And we are exciting with infrared light. Any guess? Yes. So look, we should not forget that there are other levels, energy levels. And for example, even though we are looking at these two decays, there's also this level, the 6p through 3/3, no, 3/2, that has a blue decay. So if you are not selecting the light that you are looking at, then you will see a couple of colors, and that's that's why we see red and blue in the cloud. But that is not the baddest news. The worst is that in reality we are looking to something like that, and that is not the worst, because we are looking to the we still haven't seen to the xenon levels. So there are much more levels that we really are simplifying in the picture. So that's what we have in the lab. We produced entangled photon pairs, entangled qubits, and this number is rather important. This is the bandwidth of the photons that we generate, and it's important because you would like them to interact with other atoms, and this is exactly the bandwidth of the states that you would like to interact with. So they are suitable to interact with other atoms, and therefore, they are good candidates to be messengers in between two nodes of a network. And okay, we have checked that they have non-classical statistics. We have checked that they are entangled, measuring a violation of Bell inequalities. And this is a sketch of the experiment. So we have the pump light that comes from the side. We overlap them, so everything goes in the same direction through phase matching. And with these two filters, we filter out all the light that we don't want to measure. And then we have two stations of quantum tomography. In that way, we verify that they entangle by measuring the version of Bell inequality that Aspect proposed in 92, which you basically define this coefficient that is a measurement that relates four orientations of your lambda plates here. And in our case, we measured moderate violation, which is everything. If you measure this coefficient greater than 2, then it's violating the Bell inequality. And that's we measured that. We are happy. We check, okay, they're entangled. We're fine. Next problem. And the problem now that we're looking at is that there's no means now, theoretically, to actually calculate the state that the atoms are producing. So this is a simplification that they did in Caltech, I believe. And this is a tomography that state would give. And this is what we measure. So you could say, okay, maybe you're doing wrong your experiment, but I think we're not doing it wrong. And the reason is here we have some quantities of quantum information that we measured. And well, the fidelity and the purity is okay, the fidelity is this one, and the purity is that one. Don't be bothered by the error bars. Then we realize that no one understands all error bars, so it's difficult to find a meaning of that. What I want you to see is that if you increase, for example, here, if we increase the field in the MOT, in the magneto-optical trap, then you see the purity and the fidelity decreasing a little bit. I mean, if you are kind, you will agree with that they decrease a little bit. But however, the entanglement here increases at the same time. So we believe that there's going something wrong because we might be comparing our measurement with a wrong state. And there's some reason to that. How much? 15 minutes. Okay. So in order to have entanglement, you actually need the Siemens states. And actually, you can just have entanglement if you pump with circularly polarized light. And the reason is that for you to measure entanglement, you need to not to be able to distinguish which path the photon that you're measuring is coming from. And that just happens by the selection rules that tells you that if you have sigma plus light, then you pump to the right, and if you have sigma minus light, you pump to the left. So, and then at the end, they have to go to the same Siemens states because of conservation of momentum. But it is just in that case that you would have entanglement. And that's the beauty of this atomic system, but it's also a problem. Why? Because they, on the magnetic field, you break the degeneracy, and then you don't have even in the simplification of our system, you don't have four levels. You have, guess how many? Well, in this case, if you are optimistic, you have 24. And it turns out that the problem for many two-level atoms was solved long ago, and Lambert proposed a formalism to treat them, to treat the dipole interaction. Our colleagues last year made the extension of that formalism for many atoms with as many levels as we wish, but it still is quite demanding computer-wise. So it is worth trying to see how you can simplify the problem. And if you do, you use a three-level system, which is basically what people have done so far, and you look at the counts, the clicks that you're measuring in each channel, you will see that some discrepancy, and it makes sense. So here is the power of the second pump, and every curve is you're increasing the power of the other pump, of the other pump laser. And you see that for small powers, this model fits pretty decently, but very small powers, very soon after that, it goes away. So you could say, okay, in a regime it works, but what if the best is to work in another regime? So we have been applying the formalism that our colleagues did to our system, and then we find out the way we find already something interesting. If you take in account 24 levels, and also you average through the magnetic field that they are going through, we find that the region that we miss is actually the other one, the lower power. And then to higher powers, it fits well. You will tell me you are cheating, you're putting a lot of curves, and it will most fit. But no, if you look at carefully, you should be able to find one curve that fits better in some others. In some others, not. It's not the same for the Idler. I believe this is this one, and then for the signal. And that's something that we quite not understand this, and that is because we're looking at just a one multi-level atom. We're still not being able to input the interaction with other atoms. I believe that this will improve quite a bit. Okay, so let's not forget the motivation of the quantum internet, the motivation of create hybrid quantum systems. And one idea that you could do is to take advantage that, well, actually, that's the plan worldwide, that some people, to take advantage that some of the decays of rubidium and all the alkali are in the are close to the telecommunications wavelength. So the idea would be to use that that decay to send it far away to maybe a memory, store it, with the help of another laser pulse, and then wait a little bit and release it with another laser pulse. And okay, so the general idea is it's actually very interesting, I believe, is that with the control laser pulse, you help to prepare the atoms in a certain, in a specific level, in a specific atomic state. Then you send a signal, which is the light containing information that you want to keep. And then you prepare the sample in a superposition of the two states. The whole ensemble is in a superposition of the two states. And then you release with another pulse. Now, that sounds very nice, but life is tough. We have an enemy, which is the noise. And it has two origins. One is that when you are applying, as we saw before, when you are exciting two transitions, at the same time you do four-way mixing. But here you don't want to do four-way mixing. You want to store a photon and then you want to release it. And if you're doing four-way mixing, you're generating light that will be noise for you. The other hard thing is that collisions create decoherence in the atoms, and then this time doesn't last for very long. So that's the two challenges that the enemy to defeat. It's not impossible. In Vienna, no. This is well in Basel, in the group of Philip Trulten, they managed a couple of years ago to do so. And for them, the key was to prepare to first pump the atoms, all the atoms in one Siemens level, and then perform a protocol, the protocol as I told you, with the main difference, and they found that it is key to stay detuned so you can decrease the forward mixing, noise. It actually turns out that there is an ideal detuning that they found that it works very, very nicely. They have a spontaneous parametric down conversion source with 10 times the bandwidth as our photons have. So our plans is to use the photons that we have in our source, in the source that it's already working. Well, right now it's not already working because we broke vacuum to put more rubidium. But the idea is that to look up for the best scheme that in which allows us to just store and then release a single photon in a third experiment. I just spoke about one experiment that we have in the lab, and we're building a quantum memory based on atomic gases. So we will have our first hybrid quantum system. So it seems like my time is over. So I want just to summarize. The quantum internet is being built, is being developed. And if I was you guys, I would pay attention because that means you could have a job as a physicist. And that's useful. Then the other thing the other message that the academic message that I want you to take home is that lights, photons and atoms can interchange energy through their density matrix and the help of the Poincare and the Bloch sphere. Our plans are a good example that you can both cold atoms and hot atoms can do the job. they have pros and cons, both options. Cold atoms, they have very little noise, but they are more chunky in the experiment. It takes more resources. In principle, the hot atoms can be scaled industrially a little bit more easy. And then and a big a strong detail of that relationship between the atomic coherences and the state of the light that you can create. That is a very strong point to in the favor of atoms as a source, as a good platform for the quantum internet, because you have the same precision as spectroscopy's precision in principle in order to prepare the photonic states. There's some work, there's quite a bit of work to be done there. We are understanding that, but it looks nice. And that's all I wanted to tell you.
Thank you, Daniel, for being on time. So we have time for questions. 1, 2, 12, 3.
Oh, okay. Thank you very much. Very interesting topic and talk. So I have two questions, more maybe in the engineering and not a lot in the physics. You talk about how the only information that we're able to send through these networks is polarization and polarized light. And you also said that if we made the entanglement 30 meters long, we are having luck. We are luck. And
no, it's not luck. You're doing good.
Yeah, we are doing good. So having these two problems, do you have any insights on how countries like China are able to send big information through thousands of kilometers of network? And for example, in other countries like England or in your lab, how far are we from this kind of
Okay,
technology?
so this is a big detail there. In China, they are not distributed entanglement yet. So they are not creating entanglement between two nodes kilometers apart. They are sending entangled light to different places, which is different. So they have many nodes that generate entangled light. One of them is in space. There you have free propagation because, well, it comes from a satellite. And I believe the dissipation, also you have a longer coherence length than in a fiber optics. In the fiber optics, we believe about 100 kilometers, then you need a repeater after more or less 100 kilometers. And the bottleneck in this development is the repeater. Because if you lose your information after 100 meters, how do you cross the Atlantic? No? So yeah, that's a good.
Okay, and my second question is that back on the day, a couple of semesters back, when I took quantum mechanics with you, you were talking about quantum internet and quantum information. So how are your thoughts currently nowadays about the development of quantum internet? Are we any close or something like quantum WhatsApp, or are we still like in the bottleneck making efforts?
Look, if you asked me 20 years ago, as I tell you, I would say it was science fiction. But now that you see that our networks actually happening, and all what they are missing is a repeater, it seems like it's going to happen. And the thing is that a good part of the infrastructure is already there because we already have internet. And the same optical fibers are useful. So it seems like that there's not a unique platform that's going to be the good one. You can generate photons with ions, quantum dots, molecules even. So it seems like and every platform has a better thing than the other one and a worse thing. So it seems like it is converging to have the ideal function of one platform, use it for that, and so on. So it seems to me that it's going to.
Okay, thank you very much for your presentation. You talked about this this four-way mixing noise that you are having in your experiment, and I saw an experiment in a group of in China that they use a cavity. They place the atoms in a cavity in order to avoid this kind of noise. I don't know if you have ever think about it.
I tried. I don't like much cavities.
Ah, you don't like cavities. I like too much.
No, I mean it's a little bit of a joke. It's you can do tricks with cavities and they can help a lot, but then also the experiment goes a little bit more complicated. So it's a balance. It's a balance to do it. We so far haven't considered it. Maybe in the future.
Thank you. The third question was you.
Thank you for your talk. When you were like giving your presentation, there's something that caught my eye, and well, it's like you said that there's also possible to have entangled qubits with massless particles. So like just the first thing is photons, but we also have, for example, neutrinos. So if we have like all the environment possible, the technology possible, will it be also possible to have neutrino entangled qubits? Because I mean, like they are resistant to decoherence. There can be entanglement to their oscillations between neutrino flavors, and yeah, like how will that work? Like, will you also have to like really need to see every time neutrino less double beta decays?
As far as I know, people that are not so able to manipulate very well neutrinos.
But like theoretically,
I prefer to think of something that I can do. So that's it.
Thank you. More questions? One.
Thank you for your talk. I have a question about how did you include your magnetic field on your model? Because when you're on the strap, you have like this magnetic field gradient. So I was curious on how did you include the effect?
Oh, it was not me, it was the theoreticians, but I can tell you what they ask us what sort of fields do we expect around the center of the magnetic optical trap. So we told them it's about a Gauss. So they made a calculation for a range. Like let's say we told them, okay, you might find plus minus 2 or 3 Gauss. So they made the calculation with a Gaussian distribution, special with more atoms at the center and less atoms in the wings, and then they averaged, and the average is what we see.
Okay, thank you.
More questions? We have still time. Come on, don't be shy. Another one. Oh, you are too far. Wait. Please.
Hi, my question is about the quantum memory protocols. Is there someone in particular that is preferred by, I don't know, the research groups? Like, I think there are like the simplest one, like optical delay, or like photon echo protocols. I'm not that familiar, but there is like someone preferred by for
Someone-
this kind of
Someone what?
protocol for optical memories, quantum memories.
You mean this kind of memories?
Yeah,
Um,
optical quantum memories, because there are different types of protocols, I think.
Yes, yes, yes. So I showed you the general thing. I showed you a particular one.
Yeah,
So
like
yes.
like in the works that you mentioned, like from China, uh, like they work with some particular protocol, like photon echo protocol.
Let's talk later. I don't
Yeah,
understand very
yeah.
much here.
Okay. Yeah. Thank you.
Thank you for your questions. More questions? No? I have a couple of questions. Thank you, Daniel. The first one is from, I think I saw that you measured the concurrence. So my question is, how do you do it? I mean, for concurrence, I know that it's for 2 qubits, but you have too many atoms. So how do you do it?
Okay, I didn't show. It's a more or less complicated expression for the concurrence, but everything is in terms of the density matrix,
Okay.
and then we measure the density matrix with the stock parameters.
So you reconstruct the density matrix
Yes.
with the
The
review
density
paper
matrix
that you
gives you
said.
everything.
Okay. Thank you. More questions? So I have another one. What is the meaning of your logo? Please, if you can explain us.
So this is a cloud of atoms.
Uh-huh.
These are 2 lasers, and these are the photons,
The single photons, right?
the tangled photons.
Entangled photons. Very nice logo. Okay. Let's thank Daniel again, please. Thank you. And we still have a couple of minutes before 12 o'clock to start with the next lecture. Hello. So we are going to start. Please take your seat. Come on, take your seat. We are going to start. Perfect. So now we have the last lecture of the famous quantum 2D materials. And it's in charge of Paula Giraldo from UNIANDES. So please, the floor is yours, Paula.
Yeah, thank you very much. And here I am again. I talked to you on Tuesday, I think it was, about 2D materials, and which is one of the research lines that we have in our lab. But today I want to again take you a little bit out of the topic you've been dealing with. I'm going to tell you about some new techniques that probably many of you don't know, but I want to emphasize on the importance of these techniques to study the band structure of materials. So Dr. Andres de Luna was telling you about the band structure of materials and how, for example, that's important to optics because we can, that band structure determines how light interact with matter or how materials can produce light in particular wavelengths. So today I'm going to show you how you actually reveal that kind of band structure, not limited just to 2D materials, but in general to materials. And I do that in one of the specialties of our group is to put things in very large magnetic fields. That's what we do for fun and for a living. And we take these very nice samples of materials and we put them in very, very large magnetic fields. Does someone knows how roughly is the magnetic field of the Earth that we can detect with compass? Of the order of a Gauss or 10 to the minus Tesla, something like that, of that order of magnitude. We take materials and measure them in fields even as high as 100 Tesla. So that's million times larger than the magnetic field of the Earth. Here I was in a talk about magnetic sensing with very small magnetic fields. We will be on the complete opposite side of the magnetic fields we are using. And we use these magnetic fields to review this band structure that I was telling you about. So I'm going to show you that we can take materials and measure very simple things as the resistance, the electrical resistance. And once you are at magnetic fields, these ones as large as 35 Tesla, which is this is a very, very intense magnetic field that consumes a lot of energy, actually. I'm gonna maybe tell you some technical details about this. You actually see this signal in the magnetoresistance, which is the change of the resistance as you put a magnetic field. This is different curves studied with the magnetic field at different orientations in space. And these wiggles that you see here, that's not noise. That's actually a consequence of the quantization of the electron orbits in a magnetic field. So when you put very, very strong magnetic field, you will be in that limit in which you quantize those orbits. And that quantization allows us to actually reveal very, very important information about the electronic band structure of compounds. For instance, this origin of these wiggles that are called quantum oscillations is the same origin of the quantum Hall effect. And the quantum Hall effect is a very famous effect that happens in in pure two-dimensional materials, such as graphene or some two-dimensional electron gas that are creating these gallium arsenide heterostructures. And this quantization, this is a very bad figure, sorry for the resolution, but this quantization of the whole component of the resistivity of a material is very useful, for example, for metrology application. That's actually how now the resistance, I'm sorry, of a material not material, but the resistance, the standard of a resistance according to the international system of units is defined right now through a quantum quantity, which is very nice. We use it actually to study interesting compounds like this one, which is a quasi one-dimensional material that is composed of some chains. And when we observe this material in very high magnetic fields, this effect is measured in this compound. And we see, and we can review actually the Fermi surface of this compound, which is a very important quantity for people that do condensed matter, because this is actually where all the electronic properties of a compound relies, or where they live. So I'm going to actually show you what's the technique that we use to deduce this Fermi surface, and this is summarizing a beautiful recent archive that it's somewhere around here from our group. All right, so this is the summary. If you fall asleep, then you know what I'm going to talk about. You can talk about this in the coffee break, just with this slide. But let's go into matter. All right, so I'm gonna bore you. If you don't know about this, maybe you're gonna be happy. If you do know about this, you're gonna be a little bored, but I'm gonna try to go a little fast on the basics of what happened when we put electrons and fermions in a magnetic field. So let's start with the simplest version, which is a free electron in vacuum. So we have a dispersion relation that goes as the wave vector square, which is this parabola over here. And we know that when we have a number of electrons, like in a material, we have n electrons, the exclusion principle forbids that we put 2 electrons with the same quantum numbers in a state. So we need to actually fill electrons up to certain energy. And then that highest energy that we fill, this band, the dispersion relation, is called the Fermi energy, which is a very important quantity for condensed matter physicists. This Fermi energy, in one dimension, we see a Fermi surface, which is this state at which we are at this highest energy, at the Fermi energy, which in one dimension is just 2 points at different wave vectors that represent the Fermi wave vector, which is the maximum wave vector filled with electrons. But once you are in 2D and in 3D, you create surfaces, not points, but surfaces. So a circle, if you see it in momentum space as a projection in momentum space, and a sphere in 3 dimensions. So when you have 3 electrons in a system, considering the exclusion principle, you will have these surfaces that are the highest energy levels field. All right, and this is what we understand by just ideal methods. Things are way more complicated in real material, as I'm going to show you later. These are not the Fermi surfaces that I was showing you that I'm going to get at the end. They are more complicated, but let's study the simplest case and the response of this electron gas in a magnetic field. So you start with the Schrödinger equation and you include your magnetic field effect through the vector potential here. And then you can pick some gauge that represent a magnetic field in the Z direction, which is the direction we always pick for magnetic field. So you take this gauge and then you include it into the system, and then you see that this X coordinate enters only to modify this Y momentum, and that actually the only spatial coordinate that belongs or that comes into this equation is only the X coordinate, which means that by Hamilton equations, the momentum in the Y and in the Z direction is conserved. And then we can assume, or we can postulate a free electron or a plane wave solution for the Y and the Z component of the wave function. All right, so we need to find only the solution for our wave function in the X direction, which turns out to be a very nice solution, and it's the solution of a quantum harmonic oscillator. So let's take that equation here, and we see that this is a harmonic oscillator, the second derivative, something that goes as x squared, but is displaced, and is displaced by the momentum, by the wave vector in the y direction. And we have an energy, a total energy, which actually depends or is modulated by this wave vector in the z direction. So this is a beautiful solution. So free electrons in a magnetic field behaves as quantum oscillators in terms of their spectra and their wave functions. So we see that actually this total energy, which will be this whole term here, we can put an equal to the energy spectrum of a quantum oscillator. And then we have this n number, which is very important here, and will give us the quantization of that spectrum. And we have the cyclotron frequency here that it's directly proportional to magnetic field. This probably you already know these kind of things, but I'm emphasizing this because this will be very important to understand what comes next. So our total energy, if I just take this kz term to the other side, I know that my total energy will be an oscillator energy, a quantized spectra, plus the energy of just a plane wave in the z direction. All right. So let's go here to see how that looks in momentum space. So this solution that we see here, if we see it in the y and z direction, if you see, this is like if we replace our original energy, will be the energy of a free electron in the x and y direction. This was replaced by this quantum harmonic oscillator spectrum, meaning the energies that we had here, that was field states up to the Fermi energy, which is this dotted circle that you see here, is now replaced by some circles that are actually quantized by this n number. This equation here is the equation of a circle in the x, y plane, right? So the radius of those circles will be quantized by this quantity. This will be the radius square. So meaning that this radii for this system will be actually directly proportional to the root square of the magnetic field. This means that once you are at zero magnetic field, all of these circles will be actually very close to each other. They will have radius that are very, very small, right? And separation between them, I'm going to talk the separation in a moment, between them that are very, very small. But once you turn on the magnetic field, these radii start to increase. And these circles, which are actually called Landau levels, they start to separate and to grow out with respect to what sets our chemical potential in our system, which is the original Fermi energy or a Fermi wave vector that we had in our system. So the physics, the important physics that we will get out from this will be what happens to the energy of our Landau levels with respect to the original Fermi energy that we had when we had zero magnetic field. All right. So this is what I was telling you. So it's important to actually compare the area of each of these circles with the area of the original Fermi surface in our material, this dotted line. And once we have that one of these circles have the same area than this original Fermi energy, strange things happen and important things happen. So we see that actually the coming out, and you see this problem, like we don't have just one Landau tube, right? We have multiple Landau tubes that are embedded into our Fermi energy. What we have is that originally all this circle, inside this circle, it was filled with electrons in different states. You can think of it as a continuum. But once you turn on the magnetic field, your spectra is quantized. So your density of states is quantized, and electrons now have to live in these circles over here. So if you start increasing magnetic field, the circle will start to grow, and those electrons that are actually in this last orbit here, at some point that orbit, that Landau circle, will actually match the area of your Fermi surface. And once you turn on the magnetic field a little bit more, they will go out from the Fermi surface. And once they come out and they have an energy higher than the chemical potential, then there will be problems. Well, right? Your energy of your system will start increasing, and those electrons will have to go back below the chemical potential and occupy a lowest index Landau level. So you see that this last Landau level, the most inner Landau level, is the lowest energy one, the lowest radius one, which is the index n equals 0 Landau level. And then the increasing n index is the tubes that have larger radii. So once these orbits matches the Fermi energy, then you have a matching, and you can actually calculate what's the condition for which you will have a successive coming out of two Landau tubes, meaning what will be the condition for the n equal some n orbit and the n plus 1 orbit come out of the Fermi surface. Just to calculate what's the periodicity in which this coming out of these Landau tubes is periodic in terms of what. So this is what we are going to do. So you calculate this n, index n and n plus 1. What's the condition for which they both match the Fermi surface? And then you calculate this here. You put all these terms in terms of this area. Let's remember that this area goes as the radius square, and the radii went as root square h. So the area goes proportional to h. And these will be the fields at which these two Landau levels cross the Fermi surface. All right. So you can actually deduce, just doing some algebra, that you can find that the subtraction between the field at which the n plus 1 Landau tube and the n Landau tube come out of the Fermi surface, that subtraction is actually a constant quantity for a given material with a given Fermi surface area. So this constant means that each of the Landau tubes in your system will come out with a period that goes as 1 over h, or in a period in 1 over the magnetic field, which is constant, meaning that you have a frequency of coming out of magnetic field, which will be the inverse of this period, which is given by this quantity, the inverse of this quantity here, meaning the frequency at which these tubes come out of this Fermi surface are actually proportional to the cross-sectional area of this Fermi surface. And this is the important information that we are going to use in order to deduce things from the Fermi surfaces of complicated materials. So the first thing, one important thing, the coming out of these tubes is periodic in the inverse of magnetic field. So, and you can see that once you have a very small magnetic field, the tubes come out very frequently because they are very short, they are very close to each other, they come out very often. But once you have your tubes and your magnetic field very large, so that you only have very few tubes or circles inside this Fermi surface, the rate in magnetic field at which they will come out will increase. And meaning that the periodicity is actually in the inverse of magnetic field. All right, this is called the Onsager relation, and this is what we are going to deal with from the rest of the presentation. All right. This effect of coming out of these Landau tubes is actually in a purely two-dimensional material. It's, as I told you, is what gives rise to the quantum Hall effect. So this is a two-dimensional material. If you measure Hall effect, it will not just be a straight line, like as in a just a three-dimensional free electron system or metal. It will be initially at low fields, it will be a straight line, but then it starts to take these steps or these plateaus. And these plateaus are quantized with respect to a fundamental quantity that is called the von Klitzing constant of resistance. And all these steps are given at fractions, like fractions of this von Klitzing constant. This blue one is the Hall component, and this red one is the longitudinal component, which is just the regular resistance of your material. All right, so that's what we have in 2D. And this effect is actually very important for metrology applications. In fact, this is a beautiful story. In Colombia, we have a metrology institute, like every serious country should have. We have a metrology institute, but our standards for a metrology institute are very, very old and very, what you call it, ancient. So we actually have for the electrical resistance, the definition, according to the International System of Units, of electrical resistance is a piece of metal that is embedded in oil, and they have to recalibrate it once in a while in France, and it's so complicated. This is actually how now it is defined, the quantum or the standard of electrical resistance. And we are actually working toward creating our own standards based in these gallium arsenide heterostructures and in graphene, which is the direction this metrology for the resistance is going towards. All right. So this is just one important use of all this story that I'm telling you. Now let's think about what happens actually when we talk about 3 dimensions. Once we are in 3 dimensions, we don't have circles for the Fermi surfaces. We have spheres. And this is what we have in our sphere. And for our spheres, we have actually tubes, because nothing happens in the z direction, which is the direction of where we are applying magnetic field. So we have the dispersion will be exactly the same as originally for this z direction, but in the xy plane, we will have these circles that we are talking about. And we have exactly the same relation, because in the plane perpendicular to the field, we still have circles, so everything keeps the same. An important thing to keep in mind is this Onsager relation. Our coming out of these tubes will be periodic in 1 over the magnetic field, and the frequency of that periodicity will be directly proportional to the cross-sectional area of the Fermi surface. Meaning, if we put a magnetic field in the z direction, we are probing the cross-sectional area in the plane perpendicular to that magnetic field. And we are having access to that Fermi surface in that perpendicular plane. All right. So these tubes come out, as I was telling you. This is a very old and ugly animation, but I hope it makes the point, until you actually take out the last Landau tube, and that is called the quantum limit. And interesting things happen there. These frequencies here that are of our periodic coming out, which is periodic in 1 over the magnetic field, have units of Tesla, right? Because if it's periodic in 1 over the magnetic field, the units of the frequency will be the inverse of that periodicity, which will be Tesla. So you will be seeing here all along this talk things that are 1,000 Tesla, 4,000 Tesla. So that is not the magnetic field we are applying. That's just to be clear. Those are the frequencies of our oscillations that are a measure of the cross-sectional areas of our Fermi surfaces. All right, so once we have our 3-dimensional materials, we need to actually develop, if we want to measure the whole thermodynamics and including transport, we need to calculate very seriously all thermodynamic quantities that comes from our grand canonical potential. So we take here our spectrum of energy and put it in our partition function a way to calculate this grand canonical potential. And then we come out with this formula that was developed by Lifshitz-Kosevic many years ago. So in 3 dimensions, once we put this spectra here and we develop and do all our integrals and calculation in 3 dimensions, it turns out that the coming out of these Landau tubes won't generate as the abrupt changes that we saw for the 2-dimensional case. Because in the 2-dimensional case, the coming out of the Landau tube is completely sudden, right? It just comes out, that's it. If you see here in this animation, let's see if it comes out again. The Landau tubes has it's matching some area of your Fermi surface, is touching your Fermi surface for a large amount or for a large values of fields, right? Until the last one comes out, right? So the effect of this quantization in the Landau tubes will be not as this delta function in the resistance, but it will be some cosine function, some periodic function. And this periodicity in inverse magnetic field has our frequency here, which is our Onsager relation. And there are some prefactors that will be very, very important for us to understand that I'm going to show you. So these are our quantum oscillations in 3 dimensions, our periodic functions, and all the different quantities, thermodynamic quantities, which will be derivatives or of our thermodynamic potential, will actually pick up this periodicity and this effect. For instance, the density of states, which will be the second derivative of our partition or of our thermodynamic potential as a function of the chemical potential, will have to pick up this periodic function. The magnetization, the heat capacity, every thermodynamic quantity will pick up this periodicity with magnetic field. All right. So if we measure this in the resistivity is a complicated quantity, but it is, in terms of the thermodynamic, is directly related to the density of states. So we will be probing a thermodynamic quantity through this resistance. And the effect of measuring this in the resistivity is called Shubnikov-de-Haas effect. This Shubnikov-de-Haas effect means that actually the change in resistivity, which is the magnetoresistance, the resistivity in field, and the fractional change of this with respect to the zero field case, will pick up these terms. Our cosine function, our periodic function in inverse magnetic field, and some prefactors that have very, very important physical information for our systems. And what we measure is this. So we measure some non-oscillating resistivity, which will be some background magnetoresistance that we have for our systems, and we see our wiggles, which are not noise at all. This contains very, very important information. Because if you see this, like, oh no, that's too noisy, let's do the experiment again. No, this is actually a very, very important and marvelous effect. You can actually do these measurements in the magnetization, and your magnetization will also pick up this effect, these oscillations. And this is called the Haas-Van Alphen effect. And it's a very common, there are many techniques that measure this effect in materials. All right. Now, if you have a sphere, all your cross-sectional areas of those spheres, if you put magnetic field in different directions, will be exactly the same. Meaning the frequency of oscillations will be exactly the same in every direction of space. But once you have anisotropic systems that generate anisotropic Fermi surfaces, your cross-sectional areas of your Fermi surfaces will pick up a very strong direction dependence. So that's what we do. We put magnetic fields along many, many different orientations with respect to some crystalline plane in our material. And we see that all of these curves have very different frequency components in it. And through studying how these cross-sectional areas changes with orientation, we can reconstruct the full 3-dimensional Fermi surface of our material. So let me show you an example a little simpler than the one before our measurements for these beautiful materials that I'm going to talk to you about at the end. But now let's go to a simpler material. I'm going to tell you in a minute what this simple material is. So for this simpler material, we subtract the non-oscillatory component of the magnetoresistance, and we only get the oscillatory component. And you see that this frequency is changing. You see that the maximum of these oscillations are actually varying. They happen at different magnetic fields. So you can actually track what happens to this oscillation in this different orientation. The first thing you want to do and the first information you want to retrieve is the variation of this cross-sectional area. We are going to focus on that in a minute. The second thing you can do is focus on what drives the amplitude of this cosine function, because you can have a cosine function which is large or smaller, and there are many things that affect that amplitude of your oscillations, which is this periodic function. The first one is a temperature reduction factor, which goes as the inverse of a hyperbolic sine function. From this function, you can actually directly retrieve the effective mass of carriers in your material, which has a direct connection with the mobility of your charge carriers in your compound. And that's a very, very important quantity that we care about, right? If we want to develop very fast materials, we want to develop materials that have very, very light masses so that they move with not much inertia in our system. And this effect of this effective mass is included, and we can understand it seeing what happens to the Fermi distribution once we have a temperature different than 0. So our Fermi distribution marks the sharpness of our Fermi surface, right? So this dotted circle that I was showing you in the two-dimensional case is very, very sharp only at 0 temperature. But once you have temperature, you have a thermal widening of this step function. Therefore, this coming out of these Fermi tubes won't be as abrupt as we will have at 0 temperature. And that will affect the amplitude of our periodic function, right? So therefore, we do expect temperature to affect that amplitude. And then we can measure this if we take one of these curves, for example, this one here, and we study that only curve. We can plot it as a function of inverse field, so that you see that this is actually very, very periodic in inverse magnetic field. It fits, it works perfectly. I've been doing this for many, many years, and I'm always surprised that this works so well. So this is periodic in inverse magnetic field. And if you do different temperatures, the different colors here are different temperatures that we took this magnetoresistance at. And you see that the lowest temperatures are the blue ones, and the highest temperature are the pink ones. And the amplitude of these oscillations are reduced as we increase temperature. All right. And we can fit this temperature dependence for one of these particular maxima, and we see that it fits really well this functional form, and from that we can retrieve the effective mass of carriers. Another thing that affects the sharpness of this coming out of these Landau tubes are actually something that can widen the sharpness of the Landau tubes themselves. And let's remember that these Landau tubes, the fact that we have Landau tubes is because there are electrons that are going in orbits around the magnetic field. And these orbits they are quantized in momentum space, but they are also quantized in real space. So if your electron is able to actually complete one of these full orbits around the Fermi surface, then the electron picks up this quantumness of your system really, really well. But if your electron before completing one of these orbits is scattered into another state, which is a consequence of scattering process, which in condensed matter, we put all that into some term that it's called the mean free time or the relaxation time of carriers. If we have relaxation times that are very, very short, that will affect the quantumness of our system, and the effect that has is actually a widening of our energies and our momentum resolution of our Landau tubes. So the coming out of these Landau tubes through the Fermi energy won't be as sharp in the thermodynamic quantities as we would expect. So from measuring that dependence of that amplitude with the mean free time, we can actually deduce the mean free time itself. That dependence is actually exponential. And that is the reason why you see that it's exponential in the inverse magnetic field. It's an exponential decay. So if you plot it as an inverse magnetic field, you see exactly an exponential decay for all of your curves. from that exponential decay, you can actually immediately retrieve your mean free time. And the combination of the effective mass and your relaxation time in your system is actually the ratio of those things, is the mobility of carriers in a compound. And we want to have materials with very large mobilities, right? All right. Other factors that I'm not going to speak about. Let's move on. All right. Now, let's speak about Fermi surfaces. Now, we know what happens to our systems. We talked about this one in a magnetic field. Let's talk about how we can complicate them, how materials complicate your Fermi surfaces. So this is what you have for a metal. You're only assuming some free electron model. But once you have materials that are not that free and that are within the framework of a periodic potential that gives all the ions in your lattice of your solids give. So this is an example of a material that I'm going to tell you about, lead telluride. So you start creating bands in your system. So you have these gaps as a consequence of these perturbations due to the periodic potential in your energy spectrum of your system. And depending on how you fill your bands, you can have metals, insulators, and whatnot. So let's actually consider this effect of forming bands in a compound. And we saw from Professor De Luna on Wednesday, we saw actually this spectrum for this very common semiconductor, which is gallium arsenide. So this does not look like your parabola, right? So we quickly went from the parabola to this one, just to tell you that the band structure of real material can be very complicated. And these band structures are actually framed within this quantity that is not showing here, my first Brillouin zone for some reason. But you can imagine that your momentum space have different directions that you can point at, and those directions represent these points here. So if you go from gamma to the L point, for example, you go from the center of your momentum space to the X point in certain direction of space, and you can see how your dispersions of your different bands go, all right? So when you establish a certain number of carriers into this material, you set a Fermi energy. And depending on how this Fermi energy cross your bands, you can have different Fermi surfaces in different directions of space. For instance, you can see here that your Fermi energy is crossing this band that has a minimum here in the gamma point, meaning that right at the gamma point, you will have some Fermi surface, which will be a sphere. And that sphere will be filled by carriers, right? Because we have below the Fermi energy, we have carriers. So we have here like a little pocket of carriers in momentum space. Here at the L point, we will also have a small pocket, which will be a little more anisotropic. So the Fermi surface of this material will be something like this. Some sphere at the gamma point, which is the center of momentum space, and some ellipsoids at the L points, which are the points that are in momentum space along these kind of hexagons that are formed in the first Brillouin zone in our compound. The Brillouin zone is the like the Lego unit in momentum space that we will have. All right. So this is how we form Fermi surfaces from bands, from complicated band structures. And this is for gallium arsenide. There is a compound that is very, very similar to gallium arsenide that is called lead telluride. And I'm going to tell you about lead telluride because this compound is a very important material. For instance, lead telluride is the base compound of a thermoelectric generator that is right now in Mars, the Mars rover. The Mars rover generates its energy from a mixture of a thermoelectric generator, which is a material or a cell that converts heat into electricity so that it works, right? Because in Mars, there are many dust storms, so they cover like photovoltaic panels, so they're screwed. So now they decided to do it with thermoelectric generators, and the heat is generated through some nuclear mini plant that it's on the Mars rover. But the lead telluride is the core of that thermoelectric generator. This is a very good thermoelectric material. And like, I don't know, 10 years ago, there was very few things known for real in terms of the band structure of this material. And this was very, very surprising to me. So during my PhD, that was one of my missions, to actually determine for real what the band structure of this compound is and why we can explain that it is such a good thermoelectric. So this compound has this predicted Fermi surface, and we wanted to check if that was the case. So this is a Fermi surface that forms this kind of half ellipsoids in some particular point in momentum space. So another mission that I had was not only studying the properties, the thermoelectric properties of this compound, but also the superconducting properties. It turns out that once you replace lead in this material with a little bit of thallium, this compound becomes a superconductor. And its superconductivity is very unusual. It's actually a non-conventional superconductor because according to the carrier density that it has, this, maybe some of you know, and you have talked about some condensates, the critical temperature of this condensate depends, at least for the superconducting case, in the electronic density that you have in your material. For this material, it has a very low carrier density, and yet it has a superconducting critical temperature that is actually 10 times higher than expected given its carrier density. So this material, if you put a thallium concentration above around 0.3%, this is very, very diluted. This material starts to show superconductivity with an increase in critical temperature that goes up to 1.5 Kelvin, and then you reach the solubility limit. You cannot put more thallium inside your compound. And one of the missions was to actually, from the band structure perspective, why is this material such a good superconductor? What's the mechanism for it? So this is what we did, and this is why this material is important. So you will see throughout this presentation this thallium doping into the compound. All right. So this is what we expected. Perfect ellipsoids along this particular direction of space, and we want to determine the real Fermi surface topology and volume, and we want to know the effective mass and the relaxation time that we can obtain through our quantum oscillation measurements. So this is what we are dealing with. So this is our momentum space. And we are putting a magnetic field. We start here, and then we start rotating our magnetic field in this plane, in this orientation. So from this cartoon that I did in PowerPoint, and then you can do some very simple script to actually deduce what will be the evolution of the cross-sectional areas perpendicular to the magnetic field for all these different pockets that you have in momentum space. You have a set of 4 ellipsoids in this plane and 4 in the perpendicular plane to this one in which we are rotating magnetic field. So you start with some cross-sectional area, which are translated through our Onsager relation into a frequency measured in Tesla, not meaning that we are putting 250 Tesla. These are just a measure proportional to the cross-sectional area. So we start with a frequency for all these different pockets. So if we put magnetic field like this, we are probing this cross-sectional area here, 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 and here, and we start here. Once we start rotating, and once we reach 54 degrees, we reach the minimum cross-sectional area of this ellipsoid. So we end up here for this frequency, the lowest frequency that we will measure. And then it will start to increase again once we reach 90 degrees. But this is not the only evolution for this pocket. We are actually measuring the evolution for this pocket. Once we are here for this pocket at 35 degrees, we reach the maximum cross-sectional area for this pocket. So we see this branch of evolution of frequencies for that pocket. And for the pockets that are in the plane perpendicular, we see this evolution of the frequencies. So our frequency component of the oscillations we are expecting, it's quite complex, which complex is relative. This is complex, but it's the simplest case I will show you today. All right. So that's what we did. Knowing this, we wanted to study for real what's the Fermi surface, if it holds this behavior. So we took our samples to the National High Magnetic Field Lab in Tallahassee, Florida, to put DC fields up to 35 Tesla, which in Tallahassee, only the Mag Lab consumes about half of the total power of the whole city, which is the capital of Florida. So that gets quite expensive. Not for me, for scientists, it's actually free. You just submit your proposal. It is peer reviewed. They give you a grade, and depending on your grade, you get prioritized into a list, and then you can access to this experiment. You just need to pay for your travels. That's it. They give you the cryogenics, everything. So I encourage you to actually do this. It's very nice. So we measure our system for different orientation of magnetic field up to 35 Tesla. We subtract the non-oscillatory component because we only want to know the frequency components of our signal. We plot it as a function of magnetic field for all these different orientations. Then we plot it as a function of inverse magnetic field because they are periodic in inverse magnetic field. And we take the Fourier transforms of these curves. And we see that there are peaks of these Fourier transforms, meaning that there are some periodic composition for these oscillations. And we can plot these, we can modify it to see it more beautifully, and that's in a way that we can compare it with the plots that I showed you before of the expected evolution. And we see that this color represents the intensity of the Fourier transform as a function of the orientation in space, and this will be the frequency composition. And we can compare it with our beautiful models that I showed you before for these three branches. So this is actually lead, but doped with sodium. Lead telluride doped with sodium. Sodium is like the vanilla version of dopants into this compound, meaning sodium only can do one thing. It's just an alkali metal. It can only donate one electron. That's it. It cannot do anything else. So we wanted to know, if you donate one electron, what will be the effect of that into the Fermi surface, so that we can compare it with the evolution with thallium and see actually what's different about thallium other than doping charge into the system. All right. So from this, we can actually deduce that this material does behave as this expected Fermi surface, and we can know the sizes of the cross-sectional areas. Therefore, we can know completely what's the volume of those pockets. And we can count how much charge you can fit into those pockets. And that will give you a lot of information, because you can have direct access to the number of charge carriers that you have in your system, that you can compare and do your predictions of critical temperatures and whatnot. All right. So we did this as a function of sodium concentration, meaning how if sodium dopes one hole, it dopes holes. It dopes holes into the system. If it dopes holes continuously, you can see how these sizes are evolving, right? The cross-sectional areas goes from 25 Tesla to of the order of 300 something Tesla, meaning the pockets are just getting bigger and bigger. And then you can compare it with thallium. And it turns out that with thallium, you have a continuous evolution right here for 0.15 and 0.3. But once you go from 0.3%, which is the composition at which you start getting superconductivity in the system, this evolution of these sizes becomes more and more slow. All right? And you can plot that concentration, that evolution, so you can count the number of carriers that you can fit into these pockets as a function of the concentration of thallium in your system. This is what you would expect for a vanilla dopant like sodium. And you see that this evolution is followed with the thallium doping up to the 0.3% value. But once you enter into the superconducting region, you get that your volume of your Fermi surface saturates. But the amount of carriers that you actually measure through transport, through hole transport, is actually a little larger, meaning there is an additional contribution to transport that is not coming from a Fermi surface. And that's what we call an impurity band in a material. And that impurity band seems to be responsible for the superconducting properties of this compound. So we summarize this in a couple of beautiful papers that I didn't put the reference here, but I can share it with whoever wants to know. All right. So that's an old system that was an interesting problem. But let me tell you in these last couple of minutes a more modern problem of a very interesting material that we are studying right now in our group, which is called tantalum tellurium-4 and niobium tellurium-4. And the context on why we are interested in these kind of materials is that there is in condensed matter right now, there is a big interest in understanding what happens in the intersection of topological state, electronic states in matter and correlated states of matter. For instance, the most common case that is being studied for already 2 decades, I think, is the topological superconductors. I don't know if you've heard about this, but topological superconductors means the topological states of matter. If you think on graphene or other more fancier versions of graphene right now, like topological insulators, what characterizes these systems is that actually you have some band crossings in your system that are protected by some specific symmetries that can come from either time reversal or some particular crystallographic symmetries of the space that you have in your system. These crossings are not commonly found in materials. If you think on the band formation, all this degeneracy, given the periodicity of the system, is lifted, and that gives origin to bands. So in condensed matter, these band crossing generally have to be protected by some other properties of the Hilbert space, and that gives rise to very interesting properties in some materials, like in topological insulators, in which you have an insulator in the bulk, but you have surface states that can conduct ballistically. So these have many different applications, and not only that, but it's selective on its spin. It has a chiral term that couples your momentum with your spin, so that you can have conduction of one spin in one direction and the other spin in a different direction for the surface state. So it's very nice. But how these couples, these topological states, happen or are identified, or what consequences do they have once we have correlated electronic states like the ones Julian was telling you on Monday and on Tuesday, for example, forming topological superconductors. Some of things that have been studied in this context are, for example, Majorana fermions, right? That are one of the candidates to do quantum computing based on solid state, right? And these are just some examples of materials that have been studied in this context. The particular correlated state that I care about and that has been less studied throughout the years is the charge density wave state. So charge density wave, these are some beautiful images. This is a compound called tantalum sulfur 2, I think. And these little dots that you see here are actually atoms. These are images, scanning tunneling microscopy images, in which you can actually image the charge distribution in a certain surface in a nanometric scale. So these dots are atoms, and you see that there are dots that are brighter, that are whiter than other ones that are more purple. The ones that are shown in white have more charge accumulated around them, and the ones in purple, less charge. And the charge kind of go around forming this beautiful star-shaped pattern, right? Why would charges do that? That's actually very beautiful. They organize in periodic pattern, forming what's called a charge density wave. And these charge density wave patterns in different materials can actually have different types of patterns. Like in this one, it forms some triangles. So the interesting thing here is that actually this modulation of the charge density is periodic in space. And that periodicity has the consequence of trying to make a material an insulator. Because once you localize charge, you cannot move it freely around, right? Therefore, you go from a metal, once it forms a charge density wave, the material wants to become an insulator. So the charge density wave formation has important properties important consequences in the electronic properties. This material, if you mix it with topological states of matter, are predicted to host what it's called axion physics or axion insulator. There are some words, some characteristics of quasi-particles in condensed matter, but imported from high energy physics. So this axion insulator, I'm not gonna explain to you all the details here, but they can form what's called axion strings, which are predicted to be able to host dissipationless transport, similarly to what's the nice thing about superconductivity, right? And this has important applications. And they can also form what's called chiral charge density wave, and there are some materials that are very intensely studied right now, which are these Kagome materials, which shows very specific topological charge density wave formation. That's what I am interested in. So I'm going to put my acknowledgement slide before showing you the results, just to show you that this is an effort of many, many people that have believed that this problem is actually interested. So the crystal growth is done in Colombia by members of my group and myself, and the transport properties measurements as well. We have done ARPES, angle resolve automation spectroscopy measurement to determine band structure through this light-based technique that Andres de Luna told you about a couple of days ago. We have done STM measurement, scanning tunnel spectroscopy measurement with collaborations in members or professors in Colombia and at Stanford and at Spain, and DFT calculations, computational models of this band structure with people all over the world. And then MATLAB people that help us to do this high magnetoresistance measurement. So this is a very large effort to understand globally this problem. So I'm going to go really fast around this tantalum tellurium-4 just to illustrate a little bit of the nuances of this problem. So this tantalum tellurium-4 are materials that form a quasi-1D chains in which the tantalum ions are on the center of these clusters formed by the tellurium. They are caged in these tellurium squares that are rotated with respect to each other, forming these quasi-1D structures because the interaction between tantalum and tellurium is actually covalent, but between tellurium and tellurium in the next chain are actually van der Waals. They're weak interaction. So they form quasi-1D structures. And this compound is, because of this quasi-1D structure, it turns out that quasi-1D systems are propense, or they are unstable and to the formation of charge density wave instabilities, which is what we want to study. The charge density wave in this system has not been studied directly observed, never. This was a material that was around for many years in the 60s, 70s, but never studied with modern techniques such as STM techniques. So we did images of the local charge density pattern that this material form. Is not these star shape, these David star shapes that I show you for the other compound, but they form these, I wanted to call it them bananas, but this didn't look good in the paper. So we put them cashews. So they have shapes of cashews, which is these little forms here. If you make a zoom to these, they form this little structure with a very periodic pattern all around. And these cashews are actually formed by 3 different tellurium atoms that cluster together to form this charge density wave, this periodic modulation of charge in your compound. And one of the consequences this has is that actually your material originally has this unit cell, this periodicity, given the arrangements of atoms. But once you form a charge density wave, the periodicity of the system becomes larger. The unit cell grows. And the superstructure that you form is actually 2 times the periodicity, original periodicity in one direction, and 3 times the periodicity in the other direction. So this superstructure, having this big superstructure, of course, will have effects in the band structure. But this charge density wave formation generally have very mild effects, and it generally goes along one particular direction along which this charge density wave is formed. For this material, our goal was to find what was the consequences of the establishing this charge density wave in the system in the band structure. So that's what we did. We studied this, we calculated through our collaborators the band structure of this compound, and we see that if we were not in the charge density wave, this will be the Fermi surface that we will be forming. It will look something like this. So there will be 2 different bands that will be forming your Fermi surface, forming these closed orbits in momentum space. So this green one will be like these bows or thingies, weird thingies. And then you have some flat sheet of your Fermi surface for this blue one. So this is what you would expect if you didn't have the charge density wave from the theory perspective. Plus some topological, say, some Dirac points in its band structure. That's why we are interested at studying this system, because we want to study this intersection between these 2 types of physics. All right. In the charge density wave, we expected from the theory perspective, just from the band folding of forming these superstructures. Once you form these superstructures, your periodicity, if your periodicity in real space is larger, your periodicity in momentum space has to be smaller. So meaning the original band structure that you have in a large range, you now have to fold it back to actually form a smaller periodicity in momentum space. Just from this folding, you would expect to see this band structure. And there are 6 different bands that cross the Fermi energy, which is what we are interested at, which will be this one, but only 4 of them have enough size to actually hold most of the charge in this system, which will be these 4 here. So what we did is that we actually checked whether this was the case or not. So we did some ARPEs that I'm going to skip to go straight to the point. So we grew our beautiful single crystals. This is a sample of the beautiful single crystals with morphology that actually are a testament to the unit cell, which is quasi one-dimensional. These are very elongated crystals. We put probes. Just to put you in context, this is a 1 millimeter crystal, so it's very hard to attach leads to these tiny crystals. We put current along the chain's directions, and we rotated field in the plane perpendicular to the current. And this is what we measure. And doing the same treatment that I show you for lead telluride, we did exactly the same. We took the Fourier transforms, and we rotate these Fourier transforms to have these beautiful landscapes that I show you here that we can actually directly compare to the evolution that we would expect from the theory Fermi surface that is predicted. So we did that, and we separated into regions. For example, this low field region, these are frequencies that are proportional to the cross-sectional areas, and we see that there are these kind of shapes. So the frequency evolution goes like this. And it actually correlates really well with one of the Fermi surface sections that theory predicted for the charge density wave phase, which are this one here. This one comes from the evolution of these kind of small sections here of your Fermi surface. And this one over here is the evolution that you would expect for these bellies here. So it matches really well. Or not. All right. If we now go and explore different scales of areas, so we go into this range from 200 Tesla to 1,000 Tesla, we see these ones. And this actually, the evolution of these frequencies evolved really well with the evolution you would expect for these sections that were predicted. They don't match in size. That's one thing. So these lines here show the expected evolution from theory. And the points show the evolution that we measure experimentally that are overlapped onto these regions of yellow weight. So you see that the shapes of these evolutions of dots and lines are exactly the same, but the size are slightly different. And this is a common mismatch in DFT calculations. But the important thing is that we do observe both sets of pockets, just that experimentally one is bigger and one smaller than expected from the theory, but they exist. That's what we wanted to confirm. All right. The other thing we wanted to confirm is whether we see any evidence of the non-charge density wave Fermi surface, which is what we would expect for a typical charge density wave. We would expect to have some sections of the Fermi surface that remain from the original Fermi surface, and some that are folded due to the superstructure formed from the Fermi surface. And it turns out that in ARPES measurement, they did observe some indications of these large Fermi surfaces formed from the non-charge density wave phase. We did not observe anything in transport, right? They formed these beautiful, like sad, sleepy bear type shape things, and we did not observe anything according to that. All right. We explore one plane of rotation for magnetic field, which gives us some cuts of these cross-sectional areas of Fermi surfaces. But we wanted to explore other orientations. So that's what we did. We put current along different directions on our crystals, and we rotated field in the perpendicular plane to prevent suppressing our signal from just a null Lorentz force in our electrons. So we had to think really, really hard and grow our crystals with different techniques and different configurations to be able to explore that additional plane of rotation. So we did that, and we discovered this beautiful behavior again. And from this behavior, we saw some beautiful evolutions of these cross-sectional areas. And actually, these evolutions are very consistent with a missing Fermi surface sheet that no one had observed before and had any clue about, that was predicted in theory, which are these cylindrical pockets, which show this kind of cosine, inverse cosine kind of behavior with angle, which is characteristic of these quasi-2D Fermi surface sheets. All right. So we did find an indication of that, and to end up this what I wanted to show you, we also observed in that planar rotations frequency that match the sizes of the non-charge density wave phase that many people were hunting. And we did observe some signature consistent with that frequency. It turns out that this frequency is actually not due to the non-charge density wave phase, but it has some dispersion that goes as if it was a cylindrical pocket. And this cylindrical pocket is not observed in the non-charge density wave phase. The cylindrical pocket comes from tunneling process between different Fermi surface sheets in our system. One sheet that is cylindrical and another sheet, which is this red one here, in which carriers, instead of turning in their original orbits in their own Fermi surface, they have enough energy to actually tunnel through these other Fermi surface sheets that are very close by and create very large orbits that combine different Fermi surface sheets. From these processes, we can actually extract beautiful information in terms of, because this is a tunneling process, it depends exponentially with field, which is the energy scale that you are using actually to tunnel these electrons through these Fermi surface sheets. And you can actually deduce beautiful things like the gap between these Fermi surface sheets. Because these Fermi surface sheets were formed as a consequence of the charge density wave in our system, you can actually calculate from this gap that you deduce through these measurements the gap value of that the charge density wave is creating into your system. All right. So these many things can be learned from these quantum oscillation measurements, and many physics can be deduced from this. So just to finalize, this is what we observe for this system, and this is summarized in this archive that is here, that is very recent. And then we see that actually the Fermi surface of this compound is very consistent with the DFT structural calculation. They are incorporating the physics very, very well. And this is a very important starting point to start claiming important things about the topology. If we don't know the band structure for sure, we cannot say if there are Dirac points or whether this material is topological or not. So now we know which the experimental band structure is. Now we can start elaborating on what the connection of the topology of the system with the correlated states that we are actually observing. So this is why these kind of measurements are very, very useful. All right, that's all I wanted to tell you. I hope you enjoyed, or at least took at least the few slides, the few equations that I showed you before to take home. Thank you very much.
Thank you, Paula. So time for questions. One questions. What else?
Thank you for your talk. In the reconstruction that you made for your band structure, there is a kind of a little mismatch that can be produced by how you calculate the bands with the DFT model. But have you like revisited these calculations, like to put more interactions that can explain this and even explain better your calculations?
Yeah, thank you, Ramon. That's a great question. So indeed, there is a mismatch of the sizes that we observe from our experimental and our calculated Fermi surface. Just let me go back to that, past the sleepy bear. So this one here. So there is a mismatch. That's one thing. The match for the evolutions, meaning we do have two sets of pockets with very similar topologies in the sense of their shapes in space, right? They are there. And there is a mismatch, one up, one larger and one smaller than predicted, right? So you could use, like, once you start having this mismatch, you start saying like, oh, what generally causes these mismatches are the calculation of your Fermi energy in your system. You have your band structure, but if you fill your bands more or a little less, you change the sizes of your pockets, right? So you start claiming things like, oh, materials are never stoichiometric, meaning they have defects, and these defects can actually decrease the number of charge carriers. So you can actually have a mismatch for sizes. As long as you have a match of the shapes, that's okay. But here it's interesting what you point out, that one goes down and the other one goes up, and they are both electron pockets. So it's hard to give an argument just like impurities or something else in the system. So you are right that if you can incorporate into your DFT models additional interactions or refine your model, use different approximations for your DFT calculation in order to better reproduce this band structure. But in terms of the state of the art of the capabilities of DFT prediction, this is damn good.
Thank you. Thank you for your illustrative talk. No? When you say that the Landau circles are crossing the Fermi surface, could it be possible to create the Cooper pairs from those electrons? But
that's a great question. I mean, I don't know, and I am not sure if that's something that's easy to observe. So in terms of what you are mentioning, there are two effects. The first one is that superconductivity has a strong connection with magnetic field. You would expect that if you apply strong enough magnetic field, you destroy superconductivity, and therefore you end up in your original electron gas kind of model. So it will be difficult to observe what the effect of Cooper pairs will do into this Landau quantization of your Fermi energy. But quantum oscillations, if you want to see what happens actually once you are in the superconducting state and you have your Cooper pairs, you cannot measure that through resistance, because superconductors have zero resistance, right? You will have to do it into measuring other thermodynamic quantities like heat capacity or magnetization, right? So, and people have observed that. But the amplitude of this oscillation grows exponentially with field. So if you want to observe that at low magnetic fields, the amplitude won't be that large. And if you increase your magnetic field so that you can observe it, that you suppress superconductivity. So I have not seen, but it will be just a matter of my ignorance, right? Not that it does not exist, but I have not seen personally any study that shows the effect of this Landau quantization in the superconducting state, in superconductivity. Yes, but that's actually very interesting.
Thank you, Carlos. So, more questions? Two questions.
Okay, thank you. I would like to know, how do you think that STM measurements would impact in the observation of these charge density waves?
So how do we observe through STM measurement the charges?
How the measurement process or the experiments would impact in the shape that we detect, and it maybe do not correspond with theory?
So there is an effect. So when you measure STM in this system, this was done through my collaborators. I'm not an expert on STM, but I can provide some comments about that. So go back. Okay, here. So you are right that the STM, what you do is you put an atomically thin tip and you put it close enough to your sample, but not touching, so that you can have some tunneling, and that exponential dependence of your current with the distance actually provides a great resolution to measure these. I don't know, this is picometers, but much less than picometers, so that you have the resolution of observing like the balls, the shape of the atoms, which is actually amazing. Depending on the tip you use, you could have some artifacts on some shapes that you can actually reproduce in your system. But it turns out that these shapes that we are observing, I mean, it's hard to actually judge whether this is an artifact from your tip or whether this is a real effect. There could be some effect or some deformation of the shapes we are observing that are just a matter of, it's an experimental artifact through the tip. But the thing is that the superstructures we do observe here are very, they match really well what had been observed before with X-ray diffraction measurements, with electron diffraction measurements, in terms of the periodicity of the superstructure first, in terms of how the chains are formed. So if you see, this is the crystal structure. I did not go into these details, but you can see that this is the crystal you have. Once you cut the crystal and the surface you expose is actually shown by this red line. You cut your crystal here, which forms a tellurium in the surface. You will see only tellurium atoms. You cut them here. But then once you surface from the top, you will see this structure. The tellurium atoms form actually like a zigzag pattern. And once you trimerize the niobiums that are underneath, that are actually the way the charge density wave is formed, you cluster these telluriums into this kind of zigzag pattern type thing. And this is actually what you do observe here. These are the zigzag, this is the zigzag you see, right? So you are right. I don't know, because I'm not expert, if there is a particular way of convincing yourself that this is not a tip artifact, but this is actually very consistent with what we expected before.
Yes, thank you for your presentation. I was wondering if you could tell us more about your experimental arrangements. For example, I believe you need to be rotating around the center of the crystal when you're probing with the magnetic field. How are you certain you're doing that, for example?
That's a great question, because it's actually very, very hard to do this carefully enough. So for the lead telluride, we actually studied this very carefully. So let me go back to that. Wow, I had to have too many animations. Spent too long going back. I was pointing to the wrong direction. So for this compound, actually, you see that, and I don't have the slides here. So yes, one thing is you need to have a millimeter size crystal that you can rotate it in space in the right plane, right? So that you can actually probe the evolutions that you want. And that is extremely, extremely difficult. And we do it very, I don't know, very poorly just by eye. So we take the sample holder that has some frame, and the rotator is very well aligned with that frame. And under the microscope, we need to place the crystal so that the crystals are good. And that's why we do this in crystal first, because we want to conserve the information of the directions in momentum space, the whole frame of space. So, and our single crystals are special because of that, because single crystals keep that information. It's a perfect arrangement of atoms in the directions of your unit cell. And if you have good enough quality, the morphology of your crystals will reproduce those crystalline directions. So you use the morphology of your crystal to actually align it with the frame of your sample holder. But we do that by eye. It turns out that, for example, for this system, you can have mismatches in the plane of rotation. And we model these mismatches really, really well. What you see is that actually these two branches, this one and this one, split in two, because you have, like, if you rotate at an angle, if you rotate at a high symmetry angle, they all collapse. They are degenerate in some sense. But then once you are off by some angle, they split, but you can model this very easily. So we can actually know if this is offset because of this evolution. For the tantalum tellurium 4, it actually worked really well. We didn't see any signatures of splitting of these branches. You would see that, like, if you see one of these evolutions, but you see like two lines that are separating in distance with respect to each other, not just one yellow one, but just two of them. We did not see that for the tantalum tellurium 4. And what actually helps for that system is that the crystals are very, very long, so that the alignment of those crystals is much easier than for these lead telluride that were more three-dimensional.
Okay, so let's thanks Paula again, please.
Okay, before we start, just a little announcement. We have a QR code over there in the coffee room for feedback. So if you tell us what did you like from the school, what you didn't like from the school, it would be good for us to improve. Okay, so we're going to close the course of theoretical nanophotonics, and we welcome Ricardo for his lecture. Thank you.
Okay. Yeah, I was ad-libbing that, so I cannot restart. But the basic idea is in that sense. Like, from all the talks that you guys have been seeing now, you have been checking how the current experiments, they are going to the edge of physics and moving us to a different regime by going into much sharper resolution, whether it's in space, whether it's in time. We saw some beautiful experiments on how to measure magnetic fields. And throughout this, we are seeing how the physics that you guys see in your textbooks is not that they are wrong, but that somehow they feel incomplete. We saw, for example, in Rocio's talk, how when we go beyond the mean field approximation, we can start seeing quantum droplets. We also saw from Jorge's talk, when you are going to the edge or Fermi liquids. And when it came to quantum optics and arrays, we started to see things that look like that. So for example, what I found interesting of both Luis's and Derek's talk, it was that we were starting to see this particular dipolar matter, as you guys would see in your textbook, but the dipolar matter, it had a particular structure within. We were thinking about crystals, we were adding how the dipoles would be shifting from one another. And when it came to the theoretical description, we had this part. So even though Luis keeps on claiming that what he does is not quantum, in a sense, the green function, or how the system is propagating, it looks extremely familiar as to what Derek was saying in one way. So for instance, with Luis, we saw the green function, and he was starting to show us how when you have these dipolar arrays that they are shifting around, it would be a way of explaining how the Beatles work. He's showing us how, starting from theoretical physics, he's able to both mimic and understand the behavior of things that you see in real life. Now, when we went deeper, we started to see Derek's talk, where he no longer mimics and understands, but he starts to tailor the response of materials. And he does so by choosing atoms that you can place in in particular positions. For example, he showed us how you could have an array, a 2D array to create a single atom mirror. And he started to explain to us how these experiments work. Now, there is a way to join both of them. So for example, if we had used a dressing field, we could turn Derek's spherical atoms into something that looks as an ellipse, and it starts to resemble what we started to see with the Beatles from this. Now, there is something interesting when we are seeing both theories, and is that the reason why they both resemble is that Derek is working in the single photon limit. So he considers that in a certain way, the mirror, it's absorbing a photon, and all the interesting dynamics are going to appear to this nonlinear Hamiltonian. The Hamiltonian, as Derek explained us beautifully, it already had a dephasing between the atoms, and it had a collective decay. Similarly, it looks exactly the same as this. But the other thing that is interesting from them both is that the processes that they are explaining, it is processes that respond to how you are shining light into the system, all right? So when we see the atomic mirror, in Derek's example, when the light impinges on the right, it induces a phase to the atoms that it causes a perfect reflection. Now, it might not show up quite nicely here, but if we shine light with an angle, even though we have the particular frequency that would be resonant for our mirror, some of the light is bouncing back and some of the light propagates. What I'm going to be showing you today is not going to be a different theory to this, but we are going to try to complement what's going on. So I'm not going to be working with driven systems, but I'm going to be working with systems that spontaneously keep on emitting photons. The process of spontaneous emission is one of those standard processes that you see in quantum physics. You have an atom that is excited, and eventually it's going to go down to the ground state. Just like classically, when you have a tree that grows an apple, that apple eventually is going to reach the ground. When and how it reaches the ground is what we are going to be trying to explain today. In particular, I want to think of a spontaneous decay as a process that originally you have light that it's really localized in a particular position, being an atom or an atomic ensemble, and eventually light is going to leave the system in the form of a free photon. A free photon is just going to be an electric field, electromagnetic field that just leaves the system. Why is it interesting to start looking at this problem in 2025? And the idea is that, first of all, spontaneous decay, it embodies the two building blocks of the quantum theory of noise. For starters, it tells us about the intrinsic statistical aspect of quantum mechanics, as we are going to check later on. If there was not this uncertainty within the position and momentum equivalent of light, we wouldn't have a spontaneous emission. And then it also interplays with the classical statistical aspect. Derek already hinted at this when he was saying that when you have an electromagnetic field, it has so many degrees of freedom, whether it's frequency, polarization, the angular distribution of the atoms, that we cannot simply take all that into account, and we tend to average over that. That process of averaging implies that we don't know something about the system, and we have to describe it statistically. So today, I'm going to be telling you about how we start to have an interplay between these two statistical effects, one completely classical, one quantum, and how it affects the radiation of a system. Now, the other idea basically is that we're going to have that the spontaneous decay, it's going to be dependent on the geometry of the system and the quantum noise that surrounds it. So how am I going to complement both Derek's and Luis's work? I'm going to have this non-Hermitian Hamiltonian that tells us about the dynamics of the system a la Schrödinger. It's going to be both a deterministic and coherent evolution of the system. But this coherent evolution is going to be interrupted at random times when the system starts to emit a photon. So as you guys know, if you have an excited atom, it's gonna emit randomly, right? I'm gonna add that randomness to the system to these jumps. And basically this entire talk is gonna be based on understanding these jumps. How do they connect to the Hamiltonian of the system? All right? So at the beginning, as I was telling you, what we tend to do as physicists nowadays is trying to exploit all these beautiful experiments that are around us to control the correlations that form in light and matter, but not only the spatial and the temporal ones. But I would be lying to you if I was saying that that is just something that happens with physics. It's also a problem that is happening in several areas of science. So if you want to follow the story that I'm going to show today, it doesn't always have to be with atoms, but the equivalent is going to be with fireflies. So something that happened around the 70s is that people realized that there are cooperative phenomena that are governed by universal principles. One of the beautiful experiments at the time was that if you go to a particular mountain in Colorado, you're going to have a collection of fireflies that are going to be shining on and off, just like the atoms that are emitting radiation on and off. And what happens is that these fireflies, they tend to blink at random intervals of time. But when you get together many of these fireflies, you start to see particular bursts. So the fireflies, they tend to synchronize with each other. And this synchronization leads to a cooperative phenomena that was similar to what was being searched in quantum optics in that 70s, that was superradiance. What is impressive is that this phenomena keeps on following the description that we do today. So then in 2021, people realized that it doesn't matter just the density of the fireflies, but it matters how the fireflies are spread in the forest. So what people were starting to show is that in certain regions, if it had like maybe a little bit more plants, or maybe it was a little bit more more rocky, the fireflies, even though they had the required density, they wouldn't synchronize to one another. But when the fireflies had the given geometry among them, they were able to show these pulses of light. So what I'm gonna be doing today, I'm gonna be telling you the equivalent of these butterflies, which is gonna be with quantum phenomena. In order to do this, I'm gonna have to describe you the spatial and spectral structure of the environment that surrounds the system. It's no longer gonna be a forest, but it's gonna be either atoms that are shining into free space or artificial atoms that are shining into a transmission waveguide. I have to tell you about the interaction between the system and the environment. And ultimately, I have to tell you how measuring a quantum system tends to affect the state that we are in. This is not just an academic idea, but it also has effects in the industry and what we're doing. So for example, knowing the spatial and spectral structure of the environment is gonna allow us to create better quantum simulators by matching the response of the system and trying to see how the environment would affect how it behaves. Knowing the spatial structure of an environment is crucial in recent architectures to be able to have that the atom couples a lot stronger or more efficient to a quantum mode, and ultimately being able to measure the to be able to quantify the measurement back action is going to allow us to intervene via feedback or feed-forward algorithms. So in order to show you a little bit about this talk, I'm going to follow the next outline. We're going to be the central point of everything that we're going to do today is focusing that while the quantum optical theory was based around spatial correlation, around temporal correlations at the time, this is the G2 function that you have been hearing about, anti-bunching, bunch light, squeeze light. Now, the new generation of experiments is pushing us to create an extension towards spatially extended systems, all right? The butterflies, the fireflies that are moving in the forest. Now, in order to do this, I'm going to show you a little bit of the underlying theory, what are the assumptions that we take, and also how to connect with these classical concepts that you guys are used to. In order to do this, I'm going to follow the next outline. First, I'm going to be telling you about selective decay. I changed this slide. It was super radiant decay, but I really like Darik's definition of selective decay, of how I can decide or where the light is going to be shining regardless of the rate, which, if you're trying just to follow this story, is going to tell us how does the geometry shape the radiation path of my atomic array. Next, I'm going to be telling you about individual radiation into an engineered vacuum. As I've been claiming a lot right now is spontaneous emission, it rises from quantum fluctuations. Basically, you can be thinking that there's this small random perturbation that starts an ongoing system. Think about an avalanche. In an avalanche, you're in a really cold mountain, and there can be something really small, just a fluctuation that decides whether the snow is going to fall on one side and the other. I'm going to be telling you how modern experiments are able to control these fluctuations and change what we would expect to be a natural phenomena. And ultimately, so basically, what is the role of quantum fluctuations? And ultimately, I'm going to try to join both selective decay and radiation into an engineered vacuum to tell you about collective radiation into an engineered vacuum. What I want to do at this point, if I manage to get over there, is tell you what new insights we can get from atomic arrays. What are the collective dynamics that it would have been impossible to see if we were thinking about single atom physics, and how we can exploit those current dynamics to to go through different experiments. So before I start, are there any questions? Also, I can check my watch to see how fast. All right, so let's go. Let's start with selective decay. So we know that collective decay follows from the interference of individual radiating paths. Just like if you have classical antennas, if you have the antennas in phase, they tend to have a much stronger signal than if the antennas are out of phase. These radiated paths, they can be controlled by tailoring the underlying geometry. So in this slide, I'm showing you two experiments that Now that I realize they were really recent to me, but for you guys, you must have been in high school when this appeared. And the idea was first in the French group of Antoine Brouet, what they are able to do is they have optical tweezers and they are able to control individual atoms and then shape them in whatever geometry they want. So what we are seeing here, you guys are seeing these blinking atoms. I think it's an array of 120 sites, and each one of those points is an atom. And here we have a tora, right? Then in 2022, we have I forgot the name. In the Chicago group, that they have a collection. If you notice now the light is shining in different colors. They are also able to do different atomic species. So I think in here you have that the yellow is going to be rubidium and the blue is going to be cesium. I might be wrong in that, don't quote me. But the idea is that you can trap different species of atoms, and they decided to draw the Chicago skyline just to show that you can draw whatever you want with these atoms, all right? So then this, what we want to do as a theoretician is wonder how can we describe these quantum open systems? And in order to do it, I'm going to tell you a little bit about the master equation of what Derek told you, but I'm going to be telling you about the underlying assumptions and how to obtain that. So please stop me at any time. And if you have any problems, we can just work through it. So what we want to obtain at this point is going to be the superradiant master equation. This is going to be telling us the evolution of our atomic array, represented here by a density matrix rho. And it's going to be divided into two terms. The first one was already shown by Daniel yesterday. It has a Schrödinger kind of form, but it is interesting that it has an imaginary term here that is telling us about the lowering probability of a particular, of the atoms to stay in a particular state. And we're going to have this term that looks different from anything that you guys have seen, which basically tells us about collective jumps of the system, how the light leaves the array. So in order to find out how this master equation is obtained, I tend to work with this small cartoon of the system. What we have here is we're going to have a collection of atoms. I allow the atoms to have different polarizations to make the problem as similar as we can do it to classical dipoles that you guys know. And the atoms are going to be coupled to an external environment that is going to be composed of small harmonic oscillators. This is a really good way of thinking of an electromagnetic environment where the labels of each mode is going to be the wave vector k and the polarization lambda. We have several modes. It's represented here by the lines. As we move towards the frequency, we have more of them, all right? So think about when you have just two mirrors, you have sine waves, and then as you start to spread the mirrors further and further and further apart, you start to get more and more modes close together. Now, the interesting thing is that the atom is going to be coupled to the environment following this way. Well, it might seem a little bit, well, right now it can be a little bit overwhelming. The only thing that we are saying is that if the atom goes from the ground to the excited state, it has to absorb a photon. So check it out. Atom goes ground, excited, a photon annihilates. But when the atom goes from the excited to the ground state, it has to emit a photon. What is new about this equation from the standard master equation is that we have that each one of the atoms is going to be probing their local environment. So the atoms, they tend to probe the local environment via the strength of the field. These are all field variables. And then with their dipole moment. Okay? This is what you would expect just from classical electrodynamics. So what is important here is realize that there are going to be 3 timescales that are extremely relevant for the system and to be able to separate the atoms from the environment. The first timescale is going to be the free frequency of atoms and the mole, and that has to be way higher than the coupling strength among them. So this is going to be telling us that one of the smallest time distances is going to be omega 0. That allows us to do a perturbative expansion, just like Daniel did before, and stay at second order. Why do we stay at second order? Easy. We want that the atom is going to radiate a photon and eventually see how that photon affects the atom back. So first order terms, they just tell us how the system releases an excitation to the environment. The second order terms, it tells us how the environment hits the system back. So this is going to be the minimal requirement for our equation. Now, if we are under this approximation, it would make sense that we go into what is called an interaction picture, that the system is just oscillating at the relevant variable, at the free variables of the field and the atoms. So whenever you see a tilde, is that I am in this oscillating frame. Now, the second time scale, it appears where we wouldn't expect it, and it's on the separation of the cavity modes. So you guys have, this basically is telling us the idea of a bath. So if you guys have a small glass of water and you throw a droplet of ink, the ink is gonna paint the entire water. It's gonna paint the entire water of whatever color you wanted. But as you start making the bath larger and larger and larger, dropping a single drop is gonna affect the environment less. The equivalent for that is something that we're gonna call the correlation time of the environment. And what it's telling us is basically how quickly the ink is gonna spread throughout our entire medium. This correlation time is related to how many modes we have via Fourier transform. Don't worry about those details. But what is gonna allow us to do that is to be able to consider that the environment is only evaluated at a single time. So in order to make this a lot more straight, I'm gonna consider the case that all the atoms, they are in a single point and go back to the standard quantum optics of temporal light. So we have in here our master equation. It has tildes, so you are working in this rotating frame. And what we're gonna do is two approximations that are generally called the Born and Markov approximation, which is fancy names to telling you that the reservoir remains largely unaffected by its coupling to the system. Basically, we throw a droplet of ink in the ocean, we're not gonna notice that. So in that case, we can separate the effect of the atoms, in here represented by rho, from the effect of the environment or reservoir, in here separated by R0. The second term, the second approximation, which is the Markov one, is telling us that the changes on the system, they occur on a time scale that is much smaller than this correlation time. So the correlation time of the environment is gonna be our shortest time resolution that we have. Think about an stroboscopic light, that it is going so fast that it's gonna determine the accuracy that we have. In this sense, I find that it's insane, the experiments that Daniel showed us in the morning, where he's already going to the 40 femtosecond time, which is still larger than the correlation time, but we are getting there, you know? So in this case, what we can do is that the system, instead of carrying its entire history, the history is shaded away by the environment, and then we just take the time at this. We just take, we forget this integration and take the time at the end. Yes? Sure. So you have the system and the environment, and they are exchanging excitations in a way. So if you have a really small environment, you would be able to track how whenever you lose a photon, it goes into the environment, and then it can come back to the system. All right, so that would tell you about correlations. If the system is correlated, it would make no sense. You cannot describe it properly by separating the atom from the system. All right, it's now a mixture of them both. Now, if your environment is very, very, very large, what you can expect is that you can actually differentiate what is the atom from what is the environment. That is the Born approximation in a nutshell. All right, is it better? Something else or? No. Awesome. Okay, so then if we do these two approximations, then we can do, I was gonna say classical quantum mechanics, but we're gonna do standard quantum mechanics. First, we're gonna realize, we're gonna use the Fermi golden rule, which is telling us that the probability for the atom to radiate, it depends on both the density of modes that we have in the system and its squared coupling to the environment itself. So via Fermi golden rule, we obtain the decay rate of an atom. Notice here that the decay rate, it depends on the dipole coupling strength squared, which makes sense. The atom is probing its environment via its dipole moment. If we take the square of how strongly it couples, we have this part. Then we have a term that goes to as the frequency cubed. When we are in free space, you can convince yourself that the density of modes that you have in a cubical box is gonna go as omega cubed. All right, so that's gonna be the spontaneous decay rate, which at this point, everything that we have done is this normal statistical aspect. We have only been saying that, oh, okay, if we completely disregard the effect of the environment, we would have this decay rate, this irreversible decay. But we also have what is going to be called the reservoir correlation function. That's it. How do we average out over the environment? So remember that every time you're doing quantum optics, it's you realizing that light has an intrinsic statistical aspect. What you do, if you do it mathematically, you have that A and A dagger, they do not commute. That tells you about an uncertainty in both these operators. And what it gives is that if we have a thermal environment, the number of atoms is just the thermal average of the modes. But when we have when we change the ordering of the operators, we get a +1. So even if there are no photons occupying the system, that is that NTH is going to be equal 0, there's going to be a decay. So this slide, if you're going to take something out of this talk, let it be this one. A spontaneous decay, it is an interplay of both statistical effects and quantum statistical effects. The first line, this one is telling us that we have a large environment. We cannot describe it on detail. So we have to average out. That's the decay rate. And this line is telling us, since there are intrinsic fluctuations in the system, since it is quantum, there's going to be a +1 that tells us about the spontaneous decay. So we plugged everything back into our Schrödinger evolution. And what we obtained is going to be the superradiance master equation. Basically, this is now, I think you can read it a lot better. We're going to have photon emission that occurs at a rate gamma 0 times the thermal photons +1. And we're going to have the absorption of the photons of the environment. The jump operators in this case, since all the atoms are clumped together in one spot, is just going to be just the probability, the operators that bring every atom from the excited to its ground state. So what are the interesting, what can we learn from this master equation? The first thing is going to be that a spontaneous emission can induce coherence among the atoms. All right? This was a suggestion or discovery, I don't know what to say. I'm going to go with discovery by Dickey in 1953. And what he is saying us is that the probability for the system to decay is just going to be the trace of the jump on the left and then the opposite jump on the right. So just apply the two both jump operators of the system, and this gives you the probability of a decay. So the system is going to be in an excited state. It drops a photon. Since you don't know whether the photon came from atom 1 or from atom 2, they end up in this quantum correlated state. It's going to be a maximally entangled state. And eventually, you're going to get a second click that brings you to the ground state. What is interesting is that the first click, you can convince yourself. This is how likely it is for the angular momentum to drop the system, depending on the excitations Q. What this is telling you is that as you are going closer and closer to the equator, the rate at which, closer and closer to half filling, the rate at which the photons start to radiate becomes faster and faster and faster. Therefore, super radiance. So since the correlations that form between the atoms, they start to translate into this bigger and bigger probability for the system to emit. So if you had just atoms that are really, really far apart, for example, in this little cartoon by Gross and Harosh, you're going to have that the decay rate is the standard lowering exponential that you guys are used to. But if the atoms are together, as they build up correlations, they tend to radiate light faster and faster and eventually fall down. Now, this also helps us a motivation of how to start thinking about extended systems. And if we go 40 years later after Gross and Harosh, we have a beautiful paper by Stuart Mason and Ana Senjo Garcia that they start to ask the question, imagine that we now have an atomic array or we have an inherent geometry of the system. When do you have the transition from the system? At which atomic distance will there be the difference between the system bringing a burst or falling down as an exponential that tells us about the atoms radiating independent? So if you guys wanted to ask this question, we have to go back to our cartoon and picture how do we add that the atoms are separated in space. What this does is that we now have to consider a third relevant time scale, which is telling us about the width of our atomic cloud. So what you would expect is you want that the distance between the atoms. I think I made a mistake. Yeah, so you want that the time, yeah, in here, no, that's fine. You want that the time it takes light from get to one position of the array to the other end, it is much smaller than the time that the atom exchanges excitations with the environment. Why do we want this? What we want is that as light goes from one side to the other, we just want that the basic motion of the atom is just a free motion. It's just this doing this oscillation that we are doing. So if we consider this third relevant time scale, how will our algebra change? First of all, we have to take into account that each atom is probing its local field, and we need to account for the relative positions of the environment. So consider the two most further apart atoms of the environment, and I'm going to call one of them a source and the other one a target. So if we solve the Heisenberg equation for the modes of the environment, we're going to notice that we have, this is the formal solution, the Heisenberg equation. There is a free field, how the light would have propagated if there was no atom in between. And the second one is a scattered field. So bear with me for the next slide. And what we're going to notice is that when we sum over all the modes, we have the electric field that is going to have this shape. The free part, it evolves by itself regardless of all the modes, and a scattering part, which has this form. Now, you guys are all finishing your bachelor's, starting your master's, PhD, and whatnot. And you can realize that if you do the integral over all the possible angles of the system, you're going to get the dipole pattern radiation. Okay? So I wanted to put this equation, even though it might not help you at all, but this is telling you about this standard toroidal way that a dipole radiates, both a classical and a quantum dipole. And then the interesting part is that when we do the Born and Markov approximation, that only tells us that of all the frequencies that the system can be radiating into, all the environmental modes to which it can send some information, the most relevant ones are around the atomic transition. All right? So in here we have three different integrals. One was in time, one was the angular integral, and the other one over the modes. And when we just do this in Mathematica, we obtain that the scattered field, what happens is that an atom went from its excited state to its grounded state via its Green's function. All right? So the Green function is just telling us how the atom propagates. But notice that when the field reaches, it goes from the source to the target, there's going to be a retardation, right? The atom radiates, and then the light takes a little bit of time to reach the system. This bit of time, we can take it into account by this term, and we obtain the scattering field. Notice how similar this expression is to part of the Hamiltonian that both Derek and Luis were using. It is telling us how the atoms talk to one another. There's a real part, which is telling us a van der Waals interaction, as Rosario and as I've said. And there is a second part that it's a collective scattering. Now, if I talk about the scattered field, I also have to talk about the effect of the free field. And in order to do this, what I want you is to consider just a source and all the, the free field that is going from this side crosses the source and eventually is gonna cross the target. Without going through the algebra, because you don't get much out of it, what we realize is that the free field evaluated at the target position is gonna be the free field at the source plus this retardation time. Right? Now, this is the trick of the argument, because now when we have the interaction Hamiltonian and we separate into both source, into a scatter and free field, we notice that the free field can only be taken into account at the position of a particular atom. So if the entire free field is at the position of the particular atom plus some decay rate, then we can do the whole algebra that we did before to account that if all atoms were set in one place. All right? So this is the crux. We have atoms extended in space. We realize that the free field is how it's moving from one to the other atom. And we are able to translate it from this corner to this one. All right? And now all the atomic information is going to be at the boundary. Question? All right. So we're going to have the free fields plus a term of how the atoms are talking. But if you guys remember from the previous, from the derivation of just the temporal part, we only have this effect to tell us about the quantum jumps. So what it's telling us is that when we obtain the master equation, the only thing that determines the jump operators is going to be the free field. So jump operators, they tell us about how the system decays. How the system decays tells us about how free photons are gone into the environment. Therefore, the jump operators only depend on the free photons. This is a really interesting result because we can do, we can make always, as a theoretician, I can make a transition between jump operators that are used for showing how we place detectors at different sites. But you could also do a unitary transformation that we have that the jump operators, they turn in, for example, in this case, the eigenstates of this matrix, okay? One of them is going to be completely formal. It's going to tell us how they radiate collectively in either superradiant or subradiant channels. And the other one is going to be telling us about what happens if I detect a photon at each one of these detectors. So if they are both to be consistent, we need that both jump operators have the same probability for the atom to decay once we add over all the paths. So this is going to be an interesting sanity check that the jump operators which were related to the free field, they have to correspond to the sum of all the decay channels that you obtain from the scatter. Again, don't worry about the details. Just notice that when we have a system that is spread in space and we also spread in space the detectors, there's going to be some information that we're going to get depending on how do we measure our system, right? So what happens now when we have the decay-like superradiance of two atoms that are initially involved in an excited state? So if the separation between both atoms is just going to be lambda over 2, I'm going to go with lambda over 2. We know that if we detect a photon in detector number 1, the path that the photon went from this atom to this other, from this atom to the detector is the same from the atom to the right to the detector. So the phase that you would acquire is exactly the same phase. However, if we detect a photon in detector number 2, we know that the free field had to go through a different phase. In this case, I think it's lambda over 2. In such a case that we know that the atom went through this path. The other thing that is super exciting about this is that if we detect a photon in detector 1, the probability for detector 1 to click again is massive. It's going to be the most likely one path. So most likely the system is going to follow this path. All right? So what this is telling us is that superradiant decay in when we have a collection of atoms is just going to be a race to the bottom. The system is going to be like one of these Dalton boards that you see in the fair. You drop a little bit of the excitation and it's going to be going towards different paths, but the paths tend to self-correct each other. So it generally wants to follow the same path. So Anna and Stu, they showed that when they try to work with different geometries of the system, and they realized that regardless of the of how you set your atomic array, you're gonna have a super radiant burst. Okay, so they did something in 2 dimensions. They also had an array in 1 dimension and a circular one, and in all the cases they were able to see a burst past a critical distance. I really recommend you to see this paper. You can also see what is that distance. It depends on on the dimension of the system. And also notice something interesting. I was telling you about a competition between the decay rate and the van der Waals dephasing. What is fun is that, Stu and Anna, maybe I'll send you the slides later. You can check that the difference between having the system with a Hamiltonian or without a Hamiltonian, basically the dephasing, is going to alter the dynamics, but not too much. At the beginning, all the correlations that form, they occur so fast that we don't have a chance for the system to dephase. As soon as the atoms start to dephasing, we get a photon, and that photon brings them back. Well, detection of that photon tells us that they fell at the same part, right? So in this case, basically what we have been seeing is how we can alter the decay rate and the information that we get from the atoms via their geometry. And now we're gonna go into the next step, which, if you remember, is the radiation into a broadband squeezed vacuum. Yes? Yeah. So in this, okay, yeah. In this case, in particular, the experiment is done. The simulation is done for two-level atoms, which would be the equivalent of just having, oh no, this transition. Okay. So it's gonna be that. If you try to do it towards different paths, you also have to have a conservation law and so on. But I would expect that even via different paths, since now you would like that your detector not only tells you where it clicked, but also the polarization. If you are able to resolve the polarization, I think you would be able to create an extra addition of paths. So basically how every time you detect a photon, it's telling you information about the atom via these jump operators, and the polarization is going to be included there. So you would have to apply this. Thank you. Yes. Yep. Be a little bit more. What do you mean by rest states before I start going further? Say it in Spanish and I can. Okay, got you. So maybe more than rest states, you mean like the collective states, like in the angular momentum, when you keep adding and you go from J's to sigmas? Yeah, amazing question. So what happens is that the angular momentum states, in general, they tend to be described by this amplitude, this probability amplitude, all right? So if you have like the something that follows from the Dickey ladder, you would have that the amplitude of all the states is gonna of the probability amplitude for all the atoms is gonna be 1. All right? So then you would follow the standard angular momentum rules. You could also have that in this case, since you allow for both super and superradians, that for instance, for two atoms, you would have one that has 1 and the other one that has minus. So that would bring you from that would be the equivalent to bring you from the excited to the GE. So basically what is happening is which bases you decide to apply the jump operators, it depends on how you are probing your system. All right, the collective one, the one that you want to do, you can place the jumps in that basis, but it's just gonna be a formal one. It might be really hard when you get to an experimentalist to tell him, oh, this is the way that I detected photons. What an experimentalist wants in general is these other jump operators, because you tell them the likelihood of the system to reach a particular one of these detectors and click. All right. So this would be what you would say in old quantum theory, be the Bohr. It's not complementary. I cannot forget it. That the experiment that you are doing for the system, it tells you the boundary conditions and how correlations form. All right, contextuality. This is going to be contextuality in quantum mechanics. Whatever that means, we can talk later if not satisfied. Awesome. But yeah, basically you can change from the collective operators to the operators of, well, they're both collective, but the angular momentum one to this spatial result ones. So without further ado, now what we are going to be thinking is an idea that was already mentioned by Morgan Mitchell, and it's both extremely deep when you think about it, but really easy to say. And it is that while quantum noise cannot be eliminated, it is not immune to technical manipulations. Okay? So let's see a little bit what that means. And before I go any further, what I'm going to be telling you a little bit about right now is not going to be just atoms in real space, but we're going to have artificial atoms made of superconducting circuits because it's natural. So consider first that the standard quantum limit is just a term introduced to describe the limitations on the precision of a specification of two canonically conjugate variables. That's a mouthful to say that you have the uncertainty relation. Okay? If two operators, they do not commute, they're going to follow this uncertainty relation, where this is related to the standard variation squared, the expected value, how far is your the expected value of a system from its mid. Now, when we are working with field quadratures, I'm gonna tend to try to move this from x and p that you know from the harmonic oscillator to add an arbitrary angle theta. You can always show that this thing happens. So when we have regular vacuum, we're gonna have that the uncertainty of the system is gonna be the same regardless of the quadrature that we are in. This can be shown pictorially with the Wigner distribution, which is just gonna be a blob that moves around as excitations happen. Now, when you have a squeezed vacuum, as Morgan explained beautifully, you're gonna have that some of the fluctuations are gonna be amplified. That is, we're gonna increase a point where fluctuations happen, and they are gonna be reduced in the other quadrature. Basically, we have this little sphere, and we're moving it down. Notice how how blue the sphere is. It's related to the standard deviation, right? So we have regular vacuum. We cannot get rid of its noise, but we can manipulate it. How do we do it? You guys have already seen that it's going to be basically through a parametric amplifier. Now, at this point, I just want to make a little bit of a distinction between the one that Morgan had, and I'm going to show you. First, you're going to have a pump field that has twice what is going to be called the central frequency, and we always have a vacuum input. Everything is going to be shining towards a nonlinear medium, and what we get from the output is just a squeezed light. What this squeezed light means is that we have the photonic modes that come out. They are related, their frequency, it has to be plus the pump field frequency and minus the pump field frequency. So there has to be a phase matching condition, first a temporal one that tells us that, for instance, you have the pump in blue, then the two photons that are going to be emitted, one is going to be to the blue and the other one to the red. And every time you get the photon pairs, they have to satisfy these phase matching conditions. Now, what is exciting about this mode is that if you see they are both created in pairs, which I tried to show here by the red and blue lines. And basically that tells us that the correlation of the system, when you apply two decay or creation operators, is going to have a number that is different than 0. All right? So in the experiments that Morgan was telling, they were spectroscopy experiments. And what he wanted to do is that you only have a couple of modes that are squeezed, but we want that all the modes that talk to the atom are squeezed. So we want to be able to satisfy this condition for several modes. How many? Many orders of magnitude that are bigger than the atomic radiative line. So if we do that, we're going to have a kind of a white noise. Notice that when we add over several modes, this delta function in frequency turns into a delta function in time. And these two are the, let's see, epsilon dagger epsilon that tells us about the number of photons in the mode. That's the standard that you have from the thermal. Epsilon dagger epsilon, number of photons plus 1. But we also have these 2x2 photon correlations. All right. More than that, we see that this variable is changing with time. So the correlations, they are trying to turn around just like the harmonic oscillator would do. Okay. Now, what is exciting about this kind of system was basically a prediction by Crispin-Gardiner in 1985. That is that if I have an atom and we put the polarization of the atom to be aligned with one of the faces of the atom to be aligned with the quadrature that has a lot more quantum fluctuations, then it would become a lot more likely for the system to decay, and the decay is accelerated in that phase quadrature. But the other quadrature that is going to be experiencing a lot smaller number of fluctuations is going to tend to decay slowly, right? So Crispin-Gardiner called this the inhibition of an atomic phase decay, and the atom is radiating into this broadband squeezed vacuum, and the rate of the decay changes. Now, this happens, and eventually when the system relaxes, it relaxes to a mixed state, which it shouldn't surprise us. The atom is constantly being bombarded by these photons in two at the time. So when we measure the system at the end, there's a likelihood of it to be excited or in the ground state. Now, even though this paper was published in 1985, we have to realize about the extremely hard conditions to do this in free space. In order to do it in free space, we need that all the modes, both spatial and temporal modes that are around the atom, they have to be squeezed. We also need that the atom is, well, basically that's the biggest concern. And while it couldn't be done with the technology at the time, it was done in 2013 by the Irfan Siddiqui group, and when Peter March was a postdoc there, using superconducting circuits. What is the difference between these two systems? The basic one is the creation of a parametric amplifier. This is going to be a Josephson amplifier, which allows the people in the superconducting circuit community to increase signals a lot more or create the squeeze light throughout the system. And the second one is that the artificial atom, which in here we're going to call a transmon, it only couples to the environment that is a one-dimensional mode. There's going to be a coaxial cable, just like the one you have for the TV at your house. You connect the circuit to that TV, and since we only have modes that are moving in that direction, it becomes a lot easier to cover all the spatial modes. Now, in here we see the, I wish I could make a zoom over here. So what happens, this also tells you about the importance of which observables you tend to check in an experiment. What we have here is the population of the excited state of the system. On the left, we have that the system is radiating into a normal, regular vacuum. So what they tend to do is, since you have the population, which corresponds to either the north or the southern sphere of the Bloch sphere, we want to measure phase. So what they do is just like Daniel, they use a pulse. They move it to the equator of the Bloch sphere, let the phase evolve there for a while, and then they use a second pulse and check the population of the system. Why? Because they can only measure populations. So you can only measure what happens at both equators, and you have to use pulses in a smart way to do. What they found in this beautiful experiment is that when the system is not squeezed, the decay rate, it follows the standard phase decay that you would have in regular vacuum. But when they change the degree of squeezing in the system, in fact, here the x-axis is telling you about the degree of squeezing. If they are in phase where the fluctuations are maximal, where the fluctuations are minimal, it takes a lot of time for the phase to decay. But when they are in a case that the fluctuations are maximal, the system decays super fast. So they are able to see exactly this prediction by Crispin Gardiner 40 years later. And it's just another example of how superconducting circuits are allowing us to learn a lot more about quantum optics by giving us additional probing tools. Now, their experiment was so impressive that what they were able to do is they let the experiment run for a couple of milliseconds, and then suddenly they stop everything and do a tomography of the system. So they can check how the atom is actually the path that it is following on the Bloch sphere. So this is an individual quantum trajectory telling us the path that a system had from it. It begins here and in the final state. And as a last show of force, they use this tomography to calculate the degree of squeezing that they had of their system. Now, the degree of squeezing, they found that they have basically perfect squeezing, which is related by this function, don't worry, and 0.88 photons per mole, all right? So notice how we are changing a little bit the way that we see things. Before, we were trying to probe what the atoms did by measuring the light field, and now what we are doing is we are probing the environment by measuring the atoms. Why? Because that's the natural thing to do in this architecture. So this, again, it's super new for me, but for you guys, I guess you were in primary school, 2013. So why am I telling you this 12 years later? And the question is going to be, what happens when you have a collective radiation into a broadband squeeze vacuum? This experiment, again, it starts to become relevant because now both the regular atoms and the super circuit community, they are starting to create arrays of either real or artificial atoms. So in this coaxial cable that is represented here by well, this is the transmission line. they are able to place 1, 2, 3, 5, 6, 7 superconducting circuits. They can also do it in a cavity. This was done in Australia in the Fink group, Austria in the Fink group, and this was done in Kirchmeier's group. All right. So what would happen if we also try to send the squeeze vacuum towards this system? First of all, we have to realize that the squeezing, it depends on the way that we try to change the modes. So if we send, if we have two parametric amplifiers that are counter-propagating, we would have one of the squeezed, the one from the left, for instance, is going to be a squeezed state that is rotating in that direction. The one from the right would naturally be rotating in the other direction. So if you have two waves that go in counter-rotating in counter-propagating directions, you would expect to obtain a standing wave. Now, this standing wave is really different from the ones that you guys are used to, because it's not a standing wave in intensity, but it's a standing wave in quantum noise. Right? So in here, I'm showing you the local variance of the field, and I'm representing whenever these two go to 1/2. In one case, the dark blue represents one quadrature. In the white one represents the other quadrature. So when the two of them, their variance is 1/2, we're going to have a vacuum state. When the two of them are mostly separated, we're going to have a squeezed state, right? So we have a standing wave of quantum noise. This was insane when I learned about it. And the other thing that is very interesting is that if we are probing the spatial noise of the system, basically how does the noise in one position relates to the noise into another, it's going to only take into account the squeezing via the center of mass of the systems that we are using to probe the noise. All right? So, no, sorry. Yeah, that's center of Zn plus Zm. So maybe if we want to learn more about the statistical nature of this system, the natural thing to do would be to put atoms in an array. What happens, we were really surprised, is that when the atoms are placed in such a way that they take maximally correlated photons, the atoms themselves, they tend to correlate. So in this case, we have 6 different atoms. They are all placed into positions where this is maximal by pairs. And we obtain that the atom naturally falls down into a squeezed state. When the atom reaches this squeezed state, it becomes pure. So when you have normal decay, an atom tends to race down until it gets to the bottom of the Bloch sphere. But when you have pairs of atoms probing a squeezed state, if the photons are correlated, the atoms become correlated themselves. When the atoms start to probe not the maximal squeezed states, but the thermal photons, they tend to do a normal thermal distribution in the last state, and that is a mixed state. This allowed us to start to think, how about if we can use the atomic array as a way to map the quantum correlations of the environment? So we are doing the exact same thing with that we did with the fireflies. But instead of mapping how the forest is spread, we're mapping the quantum correlations of the system. We did some magic with the master equation, and we realized that the atoms, when they are correlated, they tend to stabilize into a pure state that is entangled. And notice how the entanglement is a combination of both ground-ground and excited state, so that when photons arrive in pairs, they will not affect the system. So this starts then we did this to be able to, by fixing both the atomic separation and the center of the array, we are able to map the correlations of the atomic, of the squeezed vacuum. Now, take into account that, yeah, we were able to see the same dynamics that you would expect with single photons, but it would be impossible to do this experiment using individual atoms. You need atomic arrays to start to find systems that are correlated in pairs. You would need 3 atoms to find systems that are correlated with correlations functions of 3, 4, 5. So if we want to learn more about quantum noise, we have to go beyond creating detectors that detect light in just a single point, but detectors that get correlated by detecting light in different points. This brings us to the last, last slide of the system, and it tells us something that it's really interesting about these correlations that we have of light and matter. So when this brings you a little bit to think about why we use light itself. So in general, we tend to use the effect that light has on a system. If we want to probe what the system is doing, we want that it separates from the light field. If you want to do a measurement, you want to perturb the system the less that you can. So for example, when you have thermal light, which doesn't have a phase relation, it's just photons arriving in given times, in random times, we tend to have a Fock state of the atom. So the atom tends to also have no idea of the correlation of the system, and it goes into states of definite energy. When we have a laser, the laser sends a coherent state, and the atom tries to mimetize that state by trying to do these Rabi oscillations of the system. It has complete phase coherence. It knows nothing about the energy levels. So now when we are thinking about squeeze light, we start to realize that the atom also tends to mimic the system. So the nature of open quantum systems is not just to minimize energy, but they want to minimize the information that they interchange with the environment. That can be done, that can be written nicely into a variational principle that we can go to in another day. So one more minute, we go back to the outline and talks. I hope you can see these three different ideas with a different light, now that we have finished this. Questions?
Questions?
Yes.
Thank you for your presentation. You mentioned repeatedly the sort of analogy between the Strogat's Firefly model and this sort of system. And I was wondering, is there a critical time difference between pulses for which we don't observe the atoms being correlated? Because for fireflies, it really depends. I mean, you can stimulate the fireflies with a sort of external pulse, and there's sort of memory effects that come into play that if the two pulses are sufficiently far apart, then the fireflies don't synchronize at all to the pulse that's incoming. So do we observe that in this array of atoms?
So first of all, the fireflies are a cartoon, right? It helps me to show
Yeah, I know, but
there's a lot more quantum. It is true that if you send pulse, so everything I showed you, in a sense, it was a lot easier to vote what Derek and Luis said, because I started with a system that it's originally in everything in the excited state, and it goes down. So if I wanted to send a pulse and see how the system, in which state it starts, it's gonna change entirely how the correlations form and how it falls down the ladder. So for example, if you send a pulse that has the relative phase of the pulse when it reaches one atom or the other is -1/2. So maybe you're gonna get one photon excite. Well, that phase is gonna be imprinted in the atoms, and then how they fall down changes a little bit. So the scheme that you use to excite the atoms or the fireflies, it's gonna affect how the atoms radiate. Is that where you were going?
yes.
Say no, it's okay.
No, I was wondering if if there was a time difference between emitted pulses for which the atoms, despite the light being correlated, don't correlate between themselves.
In free space, yes. Like there's a point that they will not correlate if they are really far apart. When you are in one dimension, like in Irfan's work, you can they can be correlated at whichever length.
Thank you.
Thank you.
Thanks, Ricardo. So this may be a rather naive question, but I was wondering, how can you control the squeezeness of your vacuum in your atomic ensemble or in your atomic array? So can you control it like in directions, or how does it work?
That's an incredibly good question. And this was done in 2013 when they did the experiment with a Josephson parametric amplifier. Now in 2021, you have the traveling wave amplifiers, which are based also on Josephson junctions, and they can create a way better degree of squeezing. They have via circulators or different magic in the superconducting circuit community that allows them to select that this squeezing occurs in a particular direction or of a particular set of modes. So you can do it via external, I'm gonna call it optical apparatus, but it's microwave things.
So maybe with this space control of the squeezeness, could it be possible, I don't know, to like create selective decay or selective radiation?
So then what happens there is that you're gonna have that part of the atoms, they want to radiate to the squeezed, to a certain squeeze, and part of the atoms, they're gonna radiate to a thermal degree. So in that case, you will not find this beautiful pure state. Because what's going to happen is you're going to have a competition of both the thermal and the squeezed photons. And I think my guess is that the thermal thing is going to end up winning because you're going to go closer and closer to this back.
Thanks.
Thank you. Yes. I just asked. I'll repeat it. Yeah, exactly. It has everything to do with the vacuum fluctuations. So when we are talking about the vacuum fluctuations, you tend to talk about the fact that A and A dagger do not commute, right? So then in this case, notice that this is B dagger B, and in this case is B dagger. So this non-commuting part gives you the +1. So exactly, vacuum fluctuations is they initialize this decay process. Yeah. No, you're great. Let me start just from, for example, from this point, right? And the jump operators. So imagine that you have a detector, and the detector, the only thing that it does, it receives photons and it clicks. Okay? If your detector is very far away, the detector cannot tell you anything about which one of these two atoms radiate. So for you, whenever you receive a click, then you know that a photon was emitted, but it could have been either from atom 1 or atom 2. So then not knowing this extra information, it creates the system that you infer from that detection is this correlated state. So whenever you have like conditioned evolution, that is the evolution of a system conditioned to a particular outcome, the most natural thing is going to be a correlated state. All right? Awesome. Those were two, right? Yes. Okay. Yes. No, and so what I was trying to say there, it goes a little bit either deeper or more superficial. It depends how you want to see things. And it goes to the idea of when you try to do a measurement in a standard system, whether it's quantum or a classical one, what you want is that your measurement apparatus, it gets information from your system and it tries to disturb it the less possible. All right? So one of the things that makes laser light really important when you are doing quantum optics, and nowadays when you are working with quantum simulators or quantum computers, is that as the atom is doing Rabi oscillations induced by the laser, you don't lose any coherence from the atom. That means that when you shine laser light into an atom, the system remains separable. All right? So then that separability tells you that laser light is really good for measuring phase. Now, what is interesting about today's talk, what I find interesting about today's talk, is that depending on the statistics of your light field, different atoms tend to respond. The atoms tend to respond different. If you send thermal light, where there is no phase information, your atoms, they tend to stay into these good energy states, right? Which makes perfect sense because thermal light, it carries no information about phase, just about energy. Now, these two are well known, and as far as I know, this one isn't. Why? Because all our theory is based into individual, well, not all our theory. A lot of our theory is based on individual atoms interacting with light. But when you have atomic arrays, you start to realize like, oh, wait, they don't want to minimize either energy or phase, but in this case, they want to mimic the system by pairing between them. So the atoms, they want to separate completely from the environment, and they do so by pairing between one another. So if you have a source of light, let's say that it's not a squeeze, that you don't send photons by pairs, but you send them in fourths, then maybe 4 atoms would be the best way to measure those correlations. Yeah.
We have time for more questions. Okay, I have a question.
Yes.
What would you like to know about vacuum, to learn about vacuum? Like you said that you could use the atoms to test vacuum.
Yeah.
What would you like to learn from vacuum?
So, me personally, I would just like to understand vacuum better, but that is not a good answer. And when that doesn't convince the investors or the funding agencies, what you would like to do is tell them a little bit about this paper. So in this case, it's a collaboration between Viola in Italy and I think Will's group. And what they realize is that when you have your the transmons, they are talking to the transmission line, but your transmission line is not perfect. And there are some correlations that form between, even when it's empty in the vacuum, there are some spatial correlations that form. So what they wanted to do is they have their superconducting circuits, and they start to change where the superconducting circuit couples to the environment. And in that way, they measure the correlations that are not just the temporal standard vacuum correlations, but also the spatial correlations. They want to do this because if you know your environment really well, it allows you to create better protocols to take into account that noise. Yeah, but I just like vacuum.
Okay, if there are no questions, we thank again Ricardo. Now, our next talk, scientific talk, is by Alonso Botero from UNIANDES. ¿Está prendido esto? Creo que no. ¿Aquí? Sí. Que se ponga verde. Ahí está. Sí.
Oh. ¿Cómo? ¿Ah? Ah, okay. Okay, thank you so much to the organizers for the invitation. So I would like to talk to you about some work that I've been doing with my collaborators. Miguel Villalobos, who was an undergrad student at the University of Los Andes, Alejandra Valencia, who is here in spirit, I think, and Hubert de Guis from Lakehead University in Ontario. And the idea is, the whole project is basically establishing a connection between three things that are apparently somewhat unrelated. Okay, definitely some of them are seem to be very unrelated. The first one is just like classical interference or multiport interference. The other one is quantum multiport interference, or like the Hongo-Mandel interference. And finally, one part that I'm not going to speak about in this talk, that's the representation theory. Okay, and the unifying concept connecting these things for us is going to be these things that we call tensor power states, which you've actually seen. You've seen them mentioned, maybe not with this name, maybe like coherent, like SU2 coherent states and things like that throughout the school, but it's the same idea. So it's basically tensor powers, like a single quantum state of a single particle, but with n particles, all of them in the same state. Okay, so let me just talk a little bit about the two aspects that I want to connect in this talk is just the interference part. So in classical interference, it's essentially the same interference that we know from high school, I guess. So it's basically light that's interfering, let's say, for instance, passing through a diffraction grating or something like that. And then, when the light fronts reach a certain point, there's a mismatch in phases, and there can be constructive or destructive interference, and then you get fringes. Okay, so all of this can be understood at the level of a single photon. So that's what I want to do next. But here I want to just talk about, like, this is going to be a little bit like the standard setting that we'll be discussing in that context, which is basically we have this element here. This is what we will call the interferometer, really. This is where the interference is taking place. And over here, what we're going to have is just basically playing with the light so we can define relative phases incoming into the interferometer. And here we have like the detection, the places where the detection takes place. Okay, so, oh my. Okay, wow. Okay, so there is a beam splitter here. There's a cube here. Okay. Okay, so in the single photon picture, okay, what we'll do is we're going to think of basically a photon entering the beam splitter through one of two paths, okay, one or two. The convention that I'm going to use is that if you go straight, then you keep on in the same path, or otherwise, if you reflect, you go into the other path. So one can go from 1 to 1 straight, or 1 and reflect to 2, okay? And you have certain probability amplitudes for doing that. Or again, if you go through 2, then you have certain probability amplitudes going to that. Those are described by elements of a unitary matrix, okay? And then at the end, you just ask whether you detect the photon at one of the two detectors, and then you just square the matrix elements, and then you get the probabilities, the final probabilities. Okay. But more generally, what you can do is that you can prepare states in superpositions of entering in port number 1 or entering in port number 2. So that's why you use another beam splitter here. Okay. Let's say you have one single, like a photon source. This could be eventually a laser or something. And then you split it here, and then you play with the phases. And then, you have the two things entering the different phases. And then you get some probability out here, okay? And the way we're going to describe this process then is in terms of, a state that we're just going to parameterize with two sets of parameters, these nus, which are basically like the probability, the magnitudes of the probabilities, and phases, the phases in each one of the terms. And so the beam splitter here, okay, this invisible cube, what it does is it maps amplitudes or magnitudes and phases, 2 magnitudes and phases at the output. And the thing that's important here to highlight is the fact that as you play with the relative phase between here and here, the probabilities, the detection probabilities of the photon here change. They're sensitive to the relative phase. So basically, one way of representing that is you think of like a 2-dimensional plot, but then you plot a line that represents the normalization of the state. So the sum of the 2 magnitudes of the 2 intensities is constant. Okay, and then along this line, what you're looking at is like the difference of the probabilities on one side or the other. And as you modulate the phase, then this point over here is going to change. So take home message here. One is that you can use the interferometer to map phases here to probabilities over here. Okay, and this you can generalize to more ports. Well, here we have, for instance, situations where you have 3 ports, 3 sources coming in, and then you can maybe use beam splitters and construct some general SU3 interferometer. Okay, and then you're going to look at intensities at the other side. Okay, this is what's called the tritter. Tritter is like the 3-port generalization of a 50-50 beam splitter. And so more generally in that case, we're going to have the same thing. We're going to have a state that's parameterized with initial intensities, with initial phases, pass it through the interferometer, you get a final state, final intensities, final phases, and then you have the detection probabilities. And so this line that we had in the case of the 2-port interferometer now becomes a region in 3-dimensional space. The axes are not showing again, okay, but it doesn't matter, fortunately. But we can think of a sort of like a triangular region where a point here represents the probability vector, okay? So if you're, for instance, at one of the edges, then basically all the probability, like in this edge, all the probability is concentrated in 1, all of it in 2, or all of it in 3. The center is going to be equal probabilities, okay? And so this is what we call the probability simplex, okay? And so if you fix the initial probabilities here and you play with the phases, what's going to happen is this point over here is going to move around, okay? In the same way that we had it in the 2-port. Okay, and now when we talk about tensor power states, it's basically taking the same, like n particles all in the same state, okay? So you can think of it like a condensate of all of them in the same state, like a Bose-Einstein condensate, okay? And so when we're dealing with these types of states, what we're interested in is basically how many, we put at the detectors how many photons we detect in each detector, and then we have a distribution of detections, and then we can plot the distribution again in a simplex that you can think of it as a probability simplex. That's what we would call like an empirical probability simplex, okay? So it's just basically how many photons came through port 1, port 2, port 3. If you preserve the number of photons, then it's also a simplex. And so that distribution is going to be given by this thing over here that's called the multimonomial distribution. And the multinomial distribution has the property that it's going to concentrate on the simplex exactly at the point. If we scale the occupations, okay, so it's going to concentrate exactly at the probability vector of the single particle state, okay? And if you think of a classical, like how we describe classical light quantum mechanically, okay, we use coherent states. Now, coherent states are states that have where the number of photons is uncertain. But one of the interesting things is this, is that you can think of a coherent state as a superposition of tensor power states with a probability amplitude that's basically like a Poissonian I mean, that's giving you a Poissonian distribution. If the number of photons is very large, like in a classical situation, you're basically concentrated around a very fixed number of n. And so the statistics are very similar to a tensor power state. So I mean, like optical coherent states are very similar to, let's say, these things which you would call like SUM coherent states if you have M ports. Okay, now we go to the multiphoton interference. So what's the idea? So the quintessential experiment in multiphoton interference is this Hongu-Mandel interferometer. The significant difference here is that you have, let's say, a light source that passes through a nonlinear crystal, and so you generate pairs of photons. One photon goes into the interferometer on one arm, the other photon goes into the interferometer on the other arm, and then you can play around, in the middle, play around with the times at which the photons reach the interferometer. And so one of the surprising thing about this effect is that if you're right at the sweet spot, what happens, like if you think of like the photons arriving at the same time, okay, at the interferometer, you're gonna get both entering here, but if you look at how the photons, at the end, what happens at each one of the ports, you will never see one photon in one port and the other photon in the other port exactly at the sweet spot. So if we look at the rate of coincidence counts for these two detectors, exactly at the sweet spot, the rate goes to 0. Okay, and then as you introduce delays between the photons, then this thing goes back up. So this is a very unintuitive effect from the point of view of classical physics, because okay, again, here is our invisible beam splitter. Okay, but classically you would say, okay, I have two photons, one comes in here, probability 1/2 of going straight or reflecting. I have another photon coming here, probability of 1/2 of going straight or reflecting. I would expect, classically, okay, if they're like independent particles, okay, that actually the process that has the highest probability, half of the times, I should find one photon in one detector and the other photon in the other one. But no, what we find is, the two photons go through one of the detectors or the other, this thing that we call bunching, okay, photon bunching. Okay, and the way you describe it, let's say in terms of creation and elision operators, then is that you basically, your beam splitter is gonna put in like a linear combination of your creation operators. Okay, when you evolve, okay, you're evolving to a state that has no single occupations in the different ports. Okay, and one of the things that I'm going to try to do later is try to give you a more intuitive way of thinking about it. Okay, so this is an example. So we call this quantum interference because really what we're doing, this is really going like hitting to the center of, like Feynman picture of interfering amplitude. You can think of this process as a process where you have a probability amplitude of the photons going straight, and if you can calculate the amplitude, it gives you 1/2. And so this would be like the two processes that contribute to a situation where you have one photon detected here and one photon detected here. Okay, so either they go straight with an amplitude of 1/2, or they reflect, okay, with an amplitude of -1/2. So there is a phase difference there, okay? And then when you add the two amplitudes, you get destructive interference. Probability is 0 for that effect. Okay. Again, we can generalize this to many ports, okay? So now, I mean, if we try to put it in one sentence, what do we think is multiphoton interferometry? Okay, it's basically a situation where you're feeding to the interferometer Fock states, okay, with different occupations in the different ports, and with one particularity, and it's that there are at least 2 ports with non-zero occupation. So not everything is in the same port. Okay, if everything is in the same port, then this would not constitute multiphotonic interference. Okay, and so again, you would have like an M-port interferometer where you sort of, the interferometer, mixes these paths. Okay, and so your initial state is this Fock state, and then you have to transform that to, because of this mixing and whatever. And okay, complicated stuff. Don't want to think about it too much. That's part of the point of the talk. But the thing that happens then is the following. You can think of this in the following way. So you have an initial state described by a Fock state, and that you can plot in a simplex where you have like the occupations of the let's say here I'm going to use 3 ports. So at some point in the simplex just is telling you how many photons are going through each one of the ports. Okay. At the end, what's going to happen is these photons are going to scatter through the interferometer, and then you're going to have many possibilities, many distributions of occupations. Each one of them corresponds to a point on this simplex. And so what we would like to understand is, what is the picture that we have here? What is this probability? I mean, how does that probability look like? Okay. And so this thing is, I mean, there's lots of situations where this type of systems have been explored. And I would like to point out like one type, which is this one, where the occupations are like 1s and 0s. So if you've ever heard of boson sampling, that's the whole idea. It just falls within this whole business, but you're only dealing with occupations that are either 1 or 0 with many ports. Okay. But the problem is always going to be the same. The problem is always going to be compute those amplitudes or those probabilities. Okay. And I don't know, but I see this monster here. Okay. And start thinking, okay, suppose now I scale the number of photons and I scale the number of ports. Okay. And this doesn't seem to be like a nice project to work on. Okay. It seems to be very complicated. Okay, the combinatorics are not very appealing. Okay, there is no physical picture of what's going on. I mean, we didn't even have a physical picture in the case of the 2 photons, right? Okay, that's why it was surprising, that you had that bunching effect. So there's no like intuition that is guiding us, to make approximations or things like nothing. Okay, and the other thing is that I haven't mentioned yet is this notion of partially indistinguishable photons. So we'll get to that in a moment, but that situation, what it's going to do is it's going to complicate this problem enormously. Okay, so what do we do? Okay, so here is my suggestion. It's like we're going to use these things called tensor power expansions. And I call this the 4 noble truths. And I noticed that the 4th truth is actually labeled with a 5. So, okay. So the first truth, I mean, I don't know if you catch the reference, but the first truth is photons are bosons. Okay. Second truth, when you're dealing with bosons, the Fock state of n bosons is the n symmetric, it's a symmetric power, it's a symmetric Hilbert space. So it's a space that is permutationally invariant. So if you have n photons, the Fock space, the sector of Fock space that corresponds to n photons is one of these symmetric powers. When you have a symmetric power of some vector space, it turns out that you can always expand a vector in one of those symmetric powers. You can always expand it, actually in many ways, in terms of tensor powers of single particle states or single copy states. There's many ways of doing it, okay? So this is what we would call a tensor power expansion. And finally, the 4th truth is, okay, for any state in the symmetric space, there must be, okay, a minimal number of terms that I need to use to expand it. And so this brings us to the notion of what we call the symmetric rank of states, of, let's say, photonic states, for instance. So you have some state of n photons, whatever state it is. And so you try out all the possible ways of writing that state as a linear superposition of tensor power states. By the way, these states don't have to be orthogonal between them. I mean, it's just different states, different single particle states. Okay, and you're just asking what is the minimum number of terms that you need to use. So if you have like a tensor power state itself is one that has symmetric rank 1. Okay, now this is a problem that turns out to be difficult. Okay, but fortunately there's a solution to the set of states that are Fock states with multiple occupations. Okay, this was done by some Italian mathematicians, Carlini et al. Okay, there's some correspondence there with okay, like forms of like symmetric what do you call it, polynomials and things like that. So that's the way they proved it. But the idea basically is this: to the minimal number of terms turns out to be, I mean, the way you compute it is you look at all the occupations, you take out the biggest occupation, and then all the occupations, you add a 1 to it, and then multiply. Okay, and that's going to give you the symmetric term. So if you think of the Hongu-Mandel state, okay, you have an occupation of 1 in one port, occupation of 1 in the other port, and so that means that your symmetric rank in that case is 2. So you can never write that Fock state as like a Fock state of one single occupation in one port. Okay, so you always have superpositions of these powers. Okay, so now so this okay, so this was the example. And so this is the way you do it explicitly for the home state. Okay, this is basically one occupation in one, occupation in 2. If you think of it in terms of distinguishable particles, it's like a state that is 1, 2 plus 2, 1, linear combination. And then if you think of it like in the block sphere, like 1 being up and 2 being down, you can think of this as a superposition of 2 sigma x pluses minus 2 sigma x minuses. Okay, and if you want to understand the home effect from this picture, it's very simple, because you have the 2. Okay, so geometry. So this is x plus and x minus, and then a 50-50 beam splitter in the block sphere. What it's going to do is going to do this, and so you take 2 of these states to the North Pole, 2 of these states to the South Pole. Okay, so you get either they bunch up or they bunch down. Okay, so it's a very simple way of doing it in this case. Okay, and so one question is, what is the minimal expansion for a Fock state? And so the way you do it is so you do it with these, single particle states that we defined before. You have your amplitudes and your phases, but then you sample the phases. Okay, you can, because in general you have many phases, so you're just sampling points on the torus of the relative phases. Okay, so you basically have a sampling of the phases on the torus, and the number of points is exactly the symmetric rank. Okay, and then it's basically just, it's very simple. You're just taking the tensor power, and then you have this exponential here. So this is a little bit like a Fourier expansion of a Kronecker delta, if you think about it a little bit further. Okay, and the amplitude actually turns out to be, it's arbitrary. Okay, you can choose any amplitude you want. Here you're going to have a normalization factor, which turns out to be like the square root of the multinomial distribution. Okay, and so you have many choices of doing that, but there is one choice, and only one choice, that is like really optimal. Why? Because if you choose your nus, in other words, like the magnitudes or the intensities, the relative intensities of the incoming state to match the relative occupations of the state. So nu i's are just the ni's divided by n. This multinomial factor here becomes polynomial with the number of photons. It doesn't change exponentially. And so, you have an exponent here with n. So things are expected here to, vary exponentially. But here, everything that you have here, and here, for instance, the symmetric rank, if the number of ports is fixed, it's also polynomial. So everything here is polynomial. And you get this very nice expansion. Okay. Very nice expansion where you basically have this polynomial factor that, okay, if you want to, like get the precise numbers, you're going to have to take into account that polynomial factor. But to understand the behavior, everything is basically given in terms of this expansion over here. And so think about it, for instance, so we're going to think about it for the two-port case. In the two-port case, you only have one relative phase. So you're basically just sampling, phases on a circle, and that just corresponds to a certain number of initial states that are going to take here. Those are the ones that are labeled each one by one of these angles. So the number of samples actually depends on the occupation, okay? And then if I take like all those vectors, and then I rotate it by the rotation that the interferometer gives me, then I get something like this, okay? And then if I want to calculate probability amplitudes, what I have to do is do the same thing with the final state, okay? So now what I'm going to have is all the vectors that I have here from the initial state, once it's been rotated by the interferometer, here is the other set of vectors from the final state. And I'm just going to multiply each one, take the inner product of each one of the blue vectors with one of the red vectors and add them up with these faces over here, okay? And so what do we see? We see something we know in the Bloch sphere, if two states are not the same, then the amplitude in magnitude is less than 1. So if you have that magnitude less than 1 scaled now by an exponential to the n, that thing is just going to, just fall exponentially small. So you only get big contributions when the two circles meet. Now I have to it's a little bit more technical because you have to guarantee also that the phases, these things are complex numbers, so the phases have to be stationary at those points. And you can guarantee that because these mappings actually turn out to be Hamiltonian, and you can show that they're stationary. But the point is, everything, all the general information is just contained in these two intersections over here. And here what I'm plotting is all the terms that I have here. The height is the magnitude, and the color is the faces, and then you see these two mountains. And so the whole contribution is basically just going to come out from the things that are here, okay? And you just add them up, and you have relative faces. The relative faces are going to change, okay, depending on the final state. And so eventually you end up with a form which is this. This is a slowly varying envelope, and then you have a rapidly varying oscillating function. And so this is, okay. So I was told that because it was a PDF, it was going to come out without problems. Okay. So anyway, so there's lines here, so you can see it, so you could see it like in a bar graph, okay, like a histogram. Okay. But the point is, so it's very difficult to see here, but the way like for large numbers, the way it works, it's you have a lot of oscillations, very rapid oscillations, and then you have this slowly varying envelope. And and so every point here, you can connect it to this picture of these two cones of vectors intersecting, okay? And one of the things, okay, so like where does the amplitude come from? And then just to give you like a sense of intuition of what's going on is you're thinking of two circles on the sphere that are going to intersect. And so depending on the angles that they intersect, then the vectors that are close by are going to have larger or smaller inner products. And so that's going to modulate that envelope over here. So that's one way of understanding it from that picture. But the really nice thing is this, that you can also connect it to the classical picture in a very beautiful way. Because classically what you do is the following. You say, okay, the torus now is just like a circle, for instance, in the case of a two-port interferometer. So as I vary this relative phase here, I modulate, okay, this is what we saw before. So you can think, okay, so what happens if I sample uniformly the circle? Okay, what is the distribution that I induce? And I induce this distribution that has the shape of a smile. So that's exactly the envelope that turns out in the multiphotonic distribution. It's exactly that envelope, okay? And it gets really much nicer when you go to 3 ports or more, because in the classical picture, for instance, in 3 ports, you're sampling uniformly the torus. And so you're basically, I mean, in a way, what you're doing is you're taking the torus, you are taking up to, this is actually in the space of density matrix. So like in 3 ports, you have like an 8-dimensional, a torus in an 8-dimensional space, and then you're projecting down the torus to the diagonal elements of the density matrix. So it's basically taking a torus and squashing it on a plane. Okay, and so that they got these really interesting figures where you have holes, for instance. Okay, and you can compute the formula for the probabilities. Okay, and so they have the holes, and then you have singularities like these lines over here. So those are lines where the determinant of the map vanishes. Okay, so they're like singular lines. They're like similar to turning points where you're doing semi-classical physics. And so the beautiful thing is, okay, you use exactly the same formula that you used before, but for all these now, like in the ports, and you get exactly a behavior that is, that mimics this 2-port thing. You get like a slowly varying envelope for the quantum multiphotonic probabilities that is basically given by the classical probability, and then you get oscillations. Okay, and then you have like regions where like in the Bloch sphere, when those 2 circles don't intersect, then all the amplitudes are the magnitudes are less than 1, so those are exponentially suppressed. So those are like tunneling regions. Okay, and so those corresponds, for instance, like the hole here, that's like a tunneling region there. Okay, and so you can do calculations, and it just works out beautifully how the correspondence between the classical map and these multiphotonic probabilities. These multiphotonic probabilities, by the way, they are basically the Wigner D matrices for SUN for the symmetric representation for this. If you're familiar with Young diagrams, it's the Young diagrams that have 1 row. Okay, and I'm just going to finish very fast with talking a little bit about the situation where you have partial indistinguishability. So in the single photon picture, what you have is what you would call partial coherence. Like think of a situation where you have your source, but then depending on your path, you sort of correlate with the path another degree of freedom. Let's say, for instance, polarization. So this other degree of freedom becomes a little bit like a measurement of the path, like a which way measurement. So if there's no correlation, then you're not making a measurement and you're not losing coherence. But if you correlate one path to one, to a state of the other degree of polarization, and then the other path to an orthogonal state of polarization, then the polarization becomes like a measurement of the path. And then you must, like from a Feynman type reasoning, you must lose all type of coherence. And so you can see that, for instance, doing the same thing, we have like a relative, I think of 2 states of polarization that are not necessarily parallel nor orthogonal. And then you can think of a single particle state that in that generic case is going to be an entangled state between ports and the other in polarization. And depending on the degree of entanglement, entanglement is going to be decoherent, more entanglement, less coherence. Okay, and then you can see it, for instance, in a loss of visibility here. So as you change this visibility parameter, which is basically the inner product of the 2 polarization vectors, the amplitude of these oscillations becomes smaller and smaller until it just reaches, it's just a single line, okay, when they're completely orthogonal. So calculating multiphotonic probabilities for many photons and for partially indistinguishable photons is very difficult. Exactly. Okay, it's really complicated. The formula that I showed you before is much more complicated. But you can use this tensor power expansion again for this thing very easily. You just basically, for each one of the ports, you're thinking of, okay, each one of the ports is going to be labeled by a index I, and then there is going to be some other state in this other degree of freedom, okay, that I'm going to call gamma I, like call it like the inner degrees of freedom. Okay, and so you have this general state now where you're correlating ports to these, states of this other degree of freedom. Okay, and then what you would have to do is, okay, just look at how many photons you're detecting in each one. You're assuming that you're not resolving the other degree of freedom. So you're just counting, just like, photon number detectors, without resolving the number of how many pass through the port. Okay. The beautiful thing is you can use exactly the same expansion that we had before, exactly the same. Okay. And so this actually gives you, it's much easier to set up the calculation. Okay. And okay, so here I'll just show you things that we've done calculating. And in the classical case, you also have a map like the other one. It's just that the map gets deformed, and the less coherence you have, the map gets shrunken. Okay. But even in that situation, what you have is basically the multiphotonic probabilities mimic the classical map. One of the things that you notice, okay, is that the oscillations are gone, and they lose them very fast. I mean, the states can be almost, like the correlated states can be almost parallel, okay, and you lose the oscillations, asymptotic. And that has to do with the fact that, you basically have many contributions that are very similar to that one, but the fringes oscillate very wildly, and so they just average out. I mean, I can't go into the details here. Okay, so I hope I gave you, at least a taste of how this might be a way of gaining some intuition around multiphotonic interference. And with that, I finish with my conclusions. Tensor power expansions are a powerful way of calculating or approaching multiphotonic interference. They allow us to identify relevant terms in asymptotic expansions. They provide a very transparent semi-classical picture. They can be adapted very easily to partially indistinguishable photons. And what I did not discuss in this talk is that there is also a really beautiful connection with the representation theory of unitary groups in the asymptotic limit. Okay.
Thank you, Alonso. Any question?
So you have a probability vector, right? I mean, like P1, P2, P3, okay? But you know that that vector, so it's a vector in 3 dimensions, right? But probabilities add to 1, okay? So it's a vector of positive entries that add up to 1. So you think, first of all, it's a vector in the first octant, okay? And in the octant, you just pass the plane, P1 plus P2 plus P3 is equal to 1. And so what that gives you is, like, for 3 options, you get a triangle. And so that's the simplex. So every probability vector, you can just plot it as a point on a simplex. Okay, so it's a very simple way of plotting probabilities or distributions in general. If you have 4, then it would be like some sort of tetrahedron. 5, okay, use your imagination, but yeah, of course. So the beautiful thing, like, okay, so let's say, for instance, classically, okay. So what's going to happen is, like, every point here. So there's a simplex here that's not showing up in the transparent. There's a big triangle here. Okay, that's the simplex. And every point here corresponds to a triplet of classical intensities. Okay, and so and every point here corresponds to like 2 relative phases, right? Because you just need 2 relative phases for 3. Okay, so you choose a pair of relative phases here, and that maps to a point here. So one thing you can do is you go through all the relative phases and see what figure you get here. So this is actually an experiment that you could do in the laboratory very easily. I mean, this is classically, like classical interference. Multiphotonic would be that in this setting, you, instead of the initial intensities, you change them for initial Fock state occupations. And so preparing those Fock states is a mess. I mean, it's not very, I mean, it's very hard. You have to use like heralded photons. You can't use like many photons. I mean, you can't, so far you can't do that. But I mean, in principle, you should be able to see the connection.
More questions?
I'm sorry, which vector? For the simplex. So I'm just thinking in general, okay? Like, so think of the simplest case. Like you have a 2-port interferometer, right? Okay, and if you just have like a single photon, okay, at the end of your Mach sender, okay, the photon is going to come out through one detector or the other, okay, with certain probabilities. The probabilities have to add up to 1. So you say P1, P2 is a point on the plane, but the probabilities have to add up to 1, so they're actually on a line, okay? And so the different distributions, probability distributions that you get as you change the phases correspond to different points on that line. And so these triangles are like 3, 4, whatever port generalizations of that. Yeah.
More questions? If not, let's think.
Okay, thank you.
We have our last coffee break, and then we'll come back for the last talk.
Hello. Okay. So it's great to hear that all of you have so much energy left. So let's try to use it a little bit more and listen to Carlos Pineda from the Institute of Physics, that he's going to tell us about coarse graining and quantum dynamics in many body systems.
Okay, so thank you very much. Thanks to the organizers for inviting me to give this talk. And so this is a work that I've been doing for the last couple of years. I've been working on a new scheme for coarse graining, which of course is relevant in for cold atoms. And right now, the latest paper was about quantum dynamics, which are some interesting results when combined with coarse graining. And right now, well, this work was done with David Davalos, which was a PhD student, and these 2 undergraduate students. And right now, I also show this affiliation because I'm doing a sabbatical at the group of Marcus Huber at TU Wien. So I always start this the talks on coarse graining with this slide because it's extremely important. When we're doing physics, we're trying to describe nature, but we have to measure nature. So theories that do not match nature, well, they're just mathematics. And well, to underline that, we have the concepts of clocks and bars in relativity. In quantum mechanics, we have von Neumann postulates. And of course, these are both extremely important in quantum mechanics and in relativity. So in general, we know that limitations regarding measurement might have deep implications in the theory. So actually, what I want to study here is to understand what are the implications of not being able to measure perfectly a quantum many-body system. And I'm going to go into great detail with respect to what I mean by that. Okay? And I think this is an important problem because I think that from this, let's say, imperfect measurement, there might arise or emerge classical states or classical dynamics. Somehow that would be my dream. I'm still very far from it, but maybe it helps. And this can also imply some fundamental limitation in the use of quantum resources like entanglement and so on. And in particular for this talk, I want to ask the question, how are quantum dynamics seen through an imperfect lens? Okay. So the outline of the talk is the following. First, I'm going to present the concept of coarse graining. This is something which normally I don't detail so much, I don't explain so much, but since this is a school, I want to spend some time explaining very well what's coarse graining. And I'll skip to the volume of coarse grain states. This is an important question. And then here is the main topic, dynamics in a coarse grain system. And if time permits, then I'm going to comment on some ideas that we're working on. So let's start with that. So here we have a Richard Feynman, normal Richard Feynman, and here we have coarse grained Richard Feynman. So the way that this coarse graining was done was simply to group particles here. So this is a 480 times 420 figure with pixels, and this one is, well, only 96 times 84. So this will reduce, of course, the information you can see. And I'm going to explain everything with Richard Feynman. So here we have Feynman's eye. So it's this green square. Okay. And we're going to divide this square in little squares of 5 times 5 pixels. Okay. And then I'm going to take a look at only this blue square here. Okay. So what I'm going to assume is that I'm only going to be able to see what you're seeing in each of these blue squares. So this image would be transformed to this image, and Feynman's picture will be transformed to this picture here. Okay. So assume that we can only measure a subset of particles, the blue ones. Okay. Of course, this is classical. And the quantum mechanical equivalent will be simply to take a partial trace. Okay. And I'm going to explain a little bit more in the next slide. So say that we're observing a subset of particles. This is the simplest example of coarse graining. So say you have a multi-particle system, but you can only observe the first particle, okay, like the blue particle. So we can write the observed expected value, say, of sigma x as the following. So this is going to be the trace of sigma x with respect to the state of just the first particle, so rho 1. And you can also write this as the expected value of sigma x applied on the first particle with respect to the whole n-body state, okay? And here we have, of course, rho 1 equals to the partial trace of rho with respect to everything but 1, okay? And more generally, if you're only able to observe a subsystem tau, then we will have a similar reasoning. We can write the expected value of A as the trace of the observable M with respect to rho tau, or equivalently, the trace of M extended to the whole space and with respect to the whole state rho in the whole multi-particle system. And in this case, again, rho tau equals to the partial trace of rho with respect to everything by tau. And actually, in fact, this is the definition of the partial trace. If you start from this, then you can prove, it's in the Nissan and Chang book, that the only state, the only object that fulfills this condition for any observable M is precisely the partial trace of rho. Okay? So in this very simple case, what I will understand as coarse graining is going to be a partial trace. Okay? I'm going to be complicating everything a little bit more. Okay? So right now, I'd like to know if everything is clear. If there are questions, please do so, because I'm going to start from here. Everything is very clear? Yes, please. Here. So no, I'm assuming that when I'm observing somehow or by some reason, I'm only able to observe this square. So simply what I'm doing here is to amplify this thing here. So if you look at this area, you can only see this square. I'm assuming that. That is what, sorry? No. But actually, we're going to get to the average later. Okay. But this is simply so this color here is this color here. You can see that this is very black and this is very black. So it's not the average. Okay. Okay. And now we're going to go to a little bit more complex example. This is going to be a 2-particle example. Okay. And we're going to assume that we're going to measure, to calculate the expected value of an observable M in a 2-particle system with a Hilbert space H8 tensored HB. Okay. However, our measurement apparatus is going to measure in HA, so the particle A with certain probability, and in B with a probability 1 minus P. Yeah. So now we have like the ability or our measurement apparatus thinks that there is only one particle, but then it's not fixed. It's not always the blue particle, but sometimes it's the blue particle, sometimes it's other particle. So now let's calculate the expected value of M. So it's going to be P times M in the first subspace with respect to the whole state, and equivalently 1 tensor M with respect to the row AB. And you can calculate. Here we make use of the swap gate to express everything in terms of row AB. And then we can write down the expected value of M as an expected value of a single particle, okay? But this particle is going to be the partial trace of B, of P times row AB. So this expected value is going to be taken with respect to a state, rho prime, which is exactly P times rho plus 1 minus P as rho S, and then a partial trace over B. So here you have an average state, which is going to be between rho and then a swap version of rho. If we consider an n particle cross-graining, so n particles cross-grain to 1, and we assume that one wishes to measure a single particle observable in an n particle system, we can do exactly the same thing. And in this case, we can calculate the average value of M as the trace of M applied to the particle I with respect to the whole state. And we can transform this expression to this one here, in which we're swapping the first particle with the ith particle with probability pi. We take an average of this state, and then we take the partial trace of everything but the first particle. And this is going to be the effective one particle state that we're observing, and we can calculate the expected value of any observable M with respect to this, let's say, effective state. So this effective state is going to be, well, our coarse grain state, and it's simply going to be the average state of the one particle states of rho with probability pi. So now we're going to do, we're going to return to Feynman. So we're going to assume that we have a many-body quantum system, and in this case, we have well, a 10 times 15 particle system. And when we measure something here, some observable, we're going to assume that we're going to measure this particle, this particle, this particle, this particle, and this particle. And next time that we measure, remember that when we're doing quantum tomography, we have to do several measurements. So this, our first measurement is going to be over these particles. Our next measurement is going to be over other particles. Our next measurement is going to be over all other particles. And in this case, if we try to reconstruct our quantum many-body system, what we're going to see is effectively an average state over all these particles. And the way that we're going to express this average state is going to be via the swap operators that I showed you before. And we're going to write it in this way. We're going to swap this particle with this particle, this particle with this particle, and so on. And then we're going to take the partial trace over everything but the blue particle. So this is what we express here. So at the end, the many-body state is going to be seen as a coarse-grained version of this particle, this mega particle here, this big particle here, and so on. And this would be effectively if we're going to be grouping different particles in our system. This case here is a very simple example in the sense that the particles here, all these particles are going to be mixed with themselves. All the particles here are going to be mixed with themselves and so on. But the general case, if we have an experimental situation, it can happen, of course, that, for example, this particle is being confused with this particle. So we have to build a more complicated situation. We can have overlapping distributions. This is closer to a realistic situation, and this would lead to a smoother finding. So, for example, here I have a situation in which we have a many body system, and we have some particles here on the top, some other particles here on the bottom, and we want to do a quantum measurement, say quantum tomography of the particles on top. But sometimes we're going to mix this particle with this particle, or this particle with this particle. So what are we going to observe in this system? Actually, we can calculate in a similar way as we did before, the quantum channel. However, the details are more complicated, and I am perfectly aware that I didn't explain well the previous details, so I'm not going to attempt to explain the details of this experimental situation here. However, one can build a quantum channel, which is built by several swap gates between, for example, this particle and this particle. And at the end, we're going to trace out the odd particles, okay? So when you do a coarse graining, in this case, you can express it as what we will call a fuzzy channel applied over rho, and then a partial trace over certain particles. And there are some details which are interesting, but I don't think are not worth trying to explain right now. Okay, so one of the powerful points of our coarse graining scheme is that we can adapt it to several geometries. I showed you our geometry in the previous slides, which had like a zigzag configuration of the particles that you had in your experiment. However, you can have, for example, a spin chain. You can have a bidimensional system. You can have, I don't know, kind of a bunch particles. You can have any configuration. For example, in the IBM computer, you have very complex configurations, and you can adapt those geometries to the particular coarse grain scheme that you want. Okay? So in general, any coarse graining can be expressed as a superposition of permutations acting on your state with certain probabilities, and then partial tracing certain particles out. So this is what we call a coarse graining. Okay, and this is also there is also a very interesting situation. If you have a system and you can only see C of rho, you can only measure C of rho, and you cannot distinguish it, C of rho from rho, then what you are effectively, what you can only deal with C of rho. You cannot distinguish it from rho. So in some sense, the real state is C of rho. This is the general definition of coarse graining. It's the composition of a partial trace and a fuzzy measurement, where a fuzzy measurement is simply a convex combination of n-body permutations with certain probabilities. And I like these definitions here a lot because I think it makes sense for realistic experimental situations. It might be good for approaching a classical limit. And well, I also like it simply because we proposed it. So there are some examples here, which maybe I'm going to skip. And right now I'm going to talk about the inverse problem. And I just want to recapitulate a little bit on what I just said. Coarse graining is a map which takes you from the state of microscopic states. So here are the pure states in the n-body system, into the mixed states in the space of 3 or 4 particles, or in general, fewer particles that you have here. So you have a microscopic state here and a coarse grain state, a coarse grain space here. Here, the coarse grain map is going to take some side to a target state rho here in the coarse grain space. And however, if you take a look back, if what you observe is this state, this is what you can observe with your experimental apparatus, you really don't know what is your true microscopic state. It can be any of these red ones here. So all of these red states yield the same target state here. So the inverse problem is going to be to determine this red set and its measure given some target state here. Now, this is a very important problem because this will give us an idea of what are the most expected states that you can observe with your apparatus. And also because this is needed to calculate the effective dynamics that you're going to observe. Okay? So in general, we study the volume of the detailed space associated with any particular state of the coarse-grained space, rho TS. So if a given state here has a very large preimage, it's going to be more likely to be observed. If you assume that you have a random state here, if you have here another state, rho TS, which has a tiny preimage, this is going to be more difficult to observe. So we want to study actually the volume of this set. So the volume, the number of states which are mapped into this target state. And we hope that we have very highly peaked distributions. Okay, we managed to solve this problem for 2 qubits. It has a beautiful geometric interpretation or geometric solution, which I could show here, which I could explain here, but anyway. However, this geometric understanding doesn't let us calculate things for more particles. And for more particles, actually, we, with the help of Alonso, who's here, managed to calculate the inverse problem, the inverse volume for M particles using random matrix theory techniques. And from this, we could obtain several interesting or semi-interesting conclusions. For example, pure states are exponentially difficult to observe, which is more or less natural. And we also have an understanding of the result in terms of random walkers. However, to tell you the truth, these results here are not so exciting. What this tells us is that when you increase the number of qubits, the state most likely to be observed is the maximally mixed state. So this is a little bit boring. However, we have the hope that when we vary the geometries or the conditions under which this is calculated, we're going to get more interesting scenarios. For example, we're going to have the emergence, why not, of classical states. And now let me go into the dynamics in coarse-grained system. I hope that I can show you some beautiful pictures. So the question here is, given a coarse-grained or an imperfect apparatus, an imperfect measurement device, what are the dynamics that we're going to observe? So let me speak a little bit more about it. We know, or we think that Schrodinger's equation is the equations that in principle tell us how nature evolves. Yes? However, the measurement devices that we have to observe nature are not perfect. They're never perfect. What are the consequences of that? That is the main question that I'm going to ask. And let's keep this example. Let me formally state the problem. So here again, we have a microscopic state. And here we also have a coarse-grained map. This coarse-grained map is determined by the experimental apparatus that you have. So you have some states here. However, you're only able to observe the density matrix that you obtain after applying this coarse-grained map. Yeah? So you really don't observe psi1 or psi2, but you really observe rho effective. Okay? Then you have Schrodinger's evolution. You have evolution, unitary evolution. It can also be open a quantum channel in general. So psi1 goes into psi1 of t, psi2 goes into psi2 of t, and so on. And then again, you're not going to observe this, but rather you're going to observe the coarse-grained version of these states. So the only thing that you can observe is this thing and this thing. Okay? Rho effective and rho effective of t. And we're going to call this map gamma of t. This map is going to be c to the -1 u of t and then C. Okay, and this is going to be this guy here is going to be the inverse map, which is yet to be defined. It has some technical issues. And I want to study this gamma of T. I want to see how nature looks when my measurement apparatus is not perfect. Okay, and actually the definition of this inverse map is not trivial. Actually, in the community, we're kind of divided about which is the best option. We really don't know. So there are two possibilities, at least two possibilities. One of them is to calculate all the states, all the pre-images of this state, so all the red points here, and they calculate the average of these guys. Okay, and the average naturally can be taken with a Haar measure. So this is expressed by this thing here. Okay, actually, it's very important to put down this small bit. Or there's another possibility, which is to take the state, which has the largest entropy and that is consistent with this equation here. Now, for me personally, this one makes more sense. However, this one here is easier to calculate, far easier to calculate. And for dynamics, we're going to consider this approach. Actually, maybe these two, we know that these two are different. However, these two might coincide in the large and limit. And this is one of the problems that we want to solve. And yeah, for this talk, I'm going to take into consideration this, let's say this inverse map here. Good. Now we have the elements to start with an example. And we're going to assume that we have a spin 1/2 system, which is a magnetic field with certain frequency, omega 0. This is the ideal state, the ideal situation. However, the real situation is that, well, this is the spin. This is, let's say, the particle 0th, the particle that we have, that we want to measure. However, there are other spins behind it. And their frequencies, I don't know, random Gaussian variables with mean omega 0. We want to measure the dynamics of this particle. However, when we measure, sometimes we measure this particle or this particle or this particle or this particle. Say that we have that we're going to measure this particle with probability 1/2. And well, I don't know. I guess that if I ask people what is the expected evolution of a system that has this Hamiltonian, I guess everyone would know, right? Okay. So actually what will happen is that the ideal situation, the spin is going to precess in the Z axis in a circle like this. However, if we have imperfect instruments, so we are going to have a superposition of unitary evolutions. And what you're going to observe is that this is going to start spiraling down until it reaches this red circle here, and then it's going to stop spiraling down. It's going to end up in this limit side. So this is a very interesting effect. I think that I have never seen such an evolution of a quantum system. And we call this halted decoherence. And it's more or less intuitive to understand its dynamics. If we allow for interaction, we have more complex figures like these ones here. And we can also examine the coarse-grained dynamics of a spin chain. And actually, we obtain very, very, very beautiful pictures. I personally like very beautiful pictures. That's why I studied physics, because I like chaos, and you know that chaos has some fractals and so on. So I am extremely happy when I get pictures like this. So the dynamics, well, if you have this the value of g equal to 0, you can solve the problem exactly, and then you obtain this solution in which the waste is being diminished very fast. We understand that. And if j is greater than 0, then we cannot solve the problem exactly, but we can do numerics, and then we obtain these figures. So I have never seen such an evolution of a quantum system. You know that they are more or less boring, but this I find not boring. And of course, we have nonlinear dynamics. And yeah, it's unusual dynamics. Good. So some of the things that we want to do in the near future with this coarse graining is to study coarse graining and chaos. How do chaotic systems are seen through the lens of coarse graining, whether they look more chaotic or more integrable. And actually they look more integrable, and we're looking into that. I'm not going to explain very well this thing. This is a problem that I really want to solve, and it's the one that I explained before, these two visions of the inverse map, one with a maximum entropy principle and the other one with a Haar measure. And I would like to combine these two, or understand if these two are the same in the large n limit. And fuzzy dynamics, we also want to understand, for example, if we want to apply unitary gates to a given set of particles, but with certain probability, you don't apply them to those particles, but to a permutation of those particles. We're also working on that. And yeah, and these are the conclusions. I apologize. I know that my explanation was a little bit chaotic, and maybe it's because I'm a little bit tired. So thank you very much for your time. And I hope that maybe with the questions, some of my main points can be clarified. So please, we do have time for questions. I know that you're also tired. This is the last talk of the last day, but yeah, that's it. Thank you.
All right, so we have time for questions.
Okay, my question is the map that you define a CPTP map, and his inverse is also true?
Okay, so yes, this is a CPT map by construction, okay, because partial trace is a CPT map, and the other are unitary operations. However, the inverse is not even linear. So it's a very complicated map, and it's not CPTP. And in fact, the inverse map is the one that is responsible for having, let's say, the complexity in the dynamics, because then it deals like nonlinear dynamics. Yes. Okay, so let me unpack that a little bit. So quantum chaos is an important field. And actually, when I started my PhD, I worked in quantum chaos. However, detecting quantum chaos is not easy, and in a many-body system is even more difficult. Okay, so would it be more easy or more difficult to detect quantum chaos in these systems or not with this imperfect thing? So of course, it's going to be a problem. Actually, systems look more integrable, and I could explain a little bit more. So that question can also be translated into open quantum system chaos. Yes, of course, you can, for example, look at the spectral statistics and so on. And I would expect essentially that levels would look a little bit more random. And in that sense, it would look also more integrable. Okay, so yes, the answer is yes. You can also apply it to open quantum system, to chaotic open quantum systems.
Thank you, Carlos. So in this spatial coarse grain scheme, how are you studying, or what are your assumptions for studying the correlations between particles or non-overlapping particles between different unit cells? For example, in the Feynman picture, what are you considering for assuming that it is like a coarse grain spatial scheme?
So actually, in the first article, wait a second. Here are the references somewhere. So the first article we published like a couple of years ago, and we studied a simple system, a simple dynamic system. So these Hamiltonian infinite particles. And you can also look, for example, you can excite the spin in the middle and see how correlations propagate. So for example, you can study the entanglement between particle 5 and particle 7, and it's going to give you something. Okay? And then you can ask yourself whether after coarse graining the system, you're going to be able to observe some correlations, okay? Which I think it's what you're asking, right? And actually the answer is yes. For example, you can see here that some correlations survive. Here would be the correlations, or the correlations measured with a concurrence, so really entanglement. So if you group particles by pairs, you're going to still be able to observe this entanglement. By groups of 4, you're also going to be able to observe. You don't see it here, but unfortunately, I think it's because of the projector. But they get attenuated. I think that's more or less reasonable to expect. So yes, you can measure those things, and if you engineer the system, you can eliminate them completely, or you can preserve them a little bit more. Yes.
Thank you. This is all based on, in some sense, qubits or distinguishable particles, yes?
Yes.
But a lot of interesting many-body physics happens with indistinguishable particles. And there you might think that all of these swap operations do something very simple. Either they do the identity or they do a -1, right? Depending on. So what happens when you apply these ideas to indistinguishable particles?
Yeah, sure. So actually, I asked you the same question at lunch for your experiments. But so, of course, when you apply, let's say one of the main objects here are swap operations. If your wave function is symmetric or antisymmetric, then they do nothing. Yeah? However, in reality, if you have localized particles, then even though they're in principle indistinguishable, you can treat them as distinguishable. So I assume here that you have, say, some localized particles in space, and then I can apply here. If you have a system with truly undistinguishable particles, then this is going to be extremely boring.
Thank you, Carlos. So I have this question, like there's another sense in which you can think of coarse graining in measurements, that is, for instance, that you're not like resolving, let's say, the levels of the eigenvalues. And once you tolerate a certain fuzziness in your resolution, then you can use that fuzziness through the uncertainty principle to weaken the measurement strength. And so the disturbance on the system, right? And so I'm just wondering if you might have explored like something similar, but with this notion of coarse graining in the sense that when you make collective measurements or something like that, in a way you can also sort of weaken, I mean, you can get the same level, like signal to noise ratios or similar signal to noise ratios with weakened interactions, so that the post measurement state has high fidelity with the initial state, like sort of information disturbance trade-off in this context.
Oh, excellent question. I have not thought about it, and I think it's a good idea.
All right. So then let's thank Carlos for the talk. Right. So let's move now to the closing remarks. And first of all, I would like to thank everyone for being here. One of the most important things that we wanted to do with this summer school was to try to present you with the whole menu of what is being done in cold atoms and condensed matter physics, at least related to things that you can manipulate with light. As you have seen throughout the lectures, there are many beautiful experiments that lead to different results. And at the end, even though all these experiments, they are going, scaling in both complexity and resolution, we are all converging towards some particular kind of physics. Also, it was very important for us to show you how this physics is universal, in the sense of how we are trying to promote collaborations between our different institutes, how we want to join people from both Latin America, Europe, and other parts of the world to try to discuss all of this and try to keep on going for every 2 years. But maybe the most important thing to remember about this conference is that it is the people that make the conference. All the speakers, I would like to thank them for preparing amazing talks, to talk among yourselves to see how you could send the best information towards the students, and also present it in a holistic way. That I know you had to balance both the work that you are doing with the work that is being done in other groups, and I think you did a beautiful job. So for that, I thank you. You can clap now for the speakers. Yeah. It is also very encouraging for us, the speakers and the organizers, to see all the energy and the genuine questions that you guys presented throughout the talk. We would love for you guys to keep on doing this throughout your career. It was super encouraging for everyone that the time slots for questions were constantly filled, that it was all the students asking, coming from different backgrounds and so on. So I would like to thank you a lot for this part. Maybe give yourself a round of applause. And please remember to keep this curiosity as you are advancing in your career. It is easy as someone gets older to try to forget all of this, but what you guys are doing, it's a really special group, everything you're doing, so keep it going forward. Now, it is also important to bring the curtain back a little bit. I would like to thank Daniel Rosales for the amazing job that he did with both the Zoom, the microphones, and everything. Thank you, Daniel. Also the staff at Nabor Carrillo, especially Gerardo, but I think he's gone, which fair enough because it's Friday afternoon. And ultimately, there's also for the organizing committee, while they weren't shown as much as maybe me and Daniel, I would like to thank Giovanna for all the organization that she did. Obviously, Ricardo and Cheita, he helped a lot with all the things that you guys don't see around of the organization, but many of the students have a hotel room thanks to him. And the largest piece of the pie goes, of course, to Daniel Sahagun. He got a lot of the money for the summer school. He was always concerned about the students, how they are going to reach here. How can we maximize the number of students, get the most people from different backgrounds? So please, Daniel, stand up. Well. And I don't know about you, but I'm ready either to go home or just unwind with some beer. So thanks, everyone. We're gone.